Okay, let me also share my screen first and then we will get into it. Okay, you should be able to see my screen now. I assume yes. So today is the last day of the lecture and tomorrow will be your final presentation. So I hope you guys have already started working on something or gonna spend time today working on something. And in our last lecture today, we're gonna talk about data science and machine learning. So it's a huge disciplinary and probably like any topic that I'm teaching you today, like you can pick up any subtopic and that could be probably 40 hours lecture on that simple same topic. So it's really vast. And today we will try to like touch base and understand from very basic point of view and kind of like get into it slowly. My focus would be first telling you all the basic ideas, and first once we are through basic ideas, then we will look at the presentation and the one of the pipeline of building end-to-end models and different stages that we will discuss one by one, like and that's how we will try to proceed with today's presentation. And finally we have a small demo, uh, building machine learning model, and I will showcase a couple of libraries that you can use and build your first model. Okay, so let's get into it. Introduction to machine learning. Um, this is like overall content. We're gonna talk about AI and different stuff. Let's look into one by one. So first thing, what is AI? What is AI? What is machine learning? What is deep learning? We have all this keyword jumping around everywhere. So first thing, AI is very generic term. It has been around since 1950s or probably before that. And AI basically means you are building the system which can perform the task which in general human can perform well. So you can think of anything which you would say that, hey, I mean, I don't know how I'm very good at doing that. A baby can figure out what is an apple and what is orange, but like if you want to build a system that can figure out, it's a difficult task. But if you can build a model, if you can build the system which can in general perform the task that you would think that in general human would be better or human would be faster to perform. So that is what we are trying to build, the AI, artificial intelligence. We are building a system which has intelligence that normally human would have. So that is what AI, a big AI means. Now you can build intelligent system, artificial intelligence system through tons of ways. So there are so many ways. Deep learning, machine learning, these are just one of those ways to do that. There are also like rule-based learning where you tell the rules, you decide the rules, you build the rules, and then machine act on the rules. And there has been multiple other ways too, other statistical ways to do the artificial intelligence. So that's why. So now, if you can see on the slide, so this is something. So I work for this company called Data Robot, and our company build automated machine learning platform. We are one of the leader in the space. This is from one of the presentation that Jeremy, which is the CEO of our company, did. And I like this slide, so I keep it, and I always keep it, and I always use it whenever I can. So if you see here, in the big terms of AI umbrella, this is like all kind of stuff that you can do with the AI. And very few stuff, like very few stuffs are actually powered by boring stuff. Boring stuff means the AI which is built in traditional way, which is not so much in the market, so much in the industry. Not a lot of people are using them. They have come out of academic background, but they haven't seen too much light into the real world practical example. But still, there are some system which is being built by that way. So, like building an AI system using some boring stuff. And then if you see here in today's world, most of the system which are built, the AI systems are actually machine learning systems. What machine learning is? Machine learning is basically this is a technique of building AI where you teach machine through the examples, and then machine learn through the examples, and finally it learns through the example, and finally it act based on what it has seen in past. So machine learning basically you build the AI system which has learned from the examples, and then you can use. And then deep learning is part of the machine learning. So we will see further that in the category of machine learning, there are multiple techniques, multiple ways, multiple people have come up with the ideas to build the AI system with this technique of machine learning, learn by example. And then finally, deep learning is one of the very subset of one of the specific technique in the whole umbrella of machine learning that is being used to build the AI system. And if you see, deep learning has seen very much promising recently, especially into natural language processing. So, self-driving car, or like vision processing, or your Alexa, or Siri, language translation, text to speech, all that kind of stuff. So that whole natural language processing idea, chatbots and stuff like that. So that is all coming out very well from the deep learning model, and we'll see what deep learning is, basically a slightly in depth. But yeah, like NLP, but otherwise a traditional statistical model that you see in the wild, machine learning, the general machine learning has done well. Let's say your spam filter, which is also an AI system, a recommendation system that is also AI system. So all these examples have seen very well into machine learning space. Okay, so I hope the whole AI, machine learning, deep learning terms are clear now. AI is like very generic term, very generic idea. Machine learning is one of the way to realize that idea. There are other ways to realize that idea, but machine learning has been much more famous and much more in the market. And then deep learning is just one of the subset, or one of the way to do the machine learning. So that is like part of the machine learning and something separate out of it. Now with that, so now why we want to do AI? So Mark Cuban, one of the very famous businessmen here in US, so he says that whatever you're studying right now, if you are not getting up to speed with deep learning neural network, you will lose. Which is saying that the future will be every business, every software product you will see in future will one or the other way touch the AI and machine learning. So it's important for students to at least know what is going on in this space. Andrew Ng, he is a very famous professor in Stanford University. So what he says that he has very famous course, like everyone who is in data science probably has taken his online class. So he says that it is difficult to think of a major industry that AI will not transform. So he also says that, like every industry will be changed through the AI. AI will bring disruption in every industry, either through automation or, uh, optimization will create some job. A lot of people will lose their job. New services will be created, which will be powered by AI. Let's say you don't need to you can just talk to your bank chatbot, and you don't need to type things. You can just talk to your bank chatbot, and you can ask your bank's AI to do all the operations just by speaking to it. So there's so many examples where human interaction will be replaced by interacting with the machines, and who will be understand you what you say, and then perform the operations likewise, like Siri and Alexa, and a lot of other ways. This is just one example. A lot of automations also, a lot of optimization also, and things like that. And finally, our supreme leader, Vladimir Putin from Russia, he says that the nation that leads in AI will be the ruler of the world. So putting it out there, like in every walks of the world, and people in different industry, academic, politics, people are talking about AI and know that this is going to be the future. Okay, so now we know that AI is important, and so what all we can do with the AI? So basically, AI can do something called predictive modeling analytics, natural language processing, recommendation engine, and clustering. Now, what is predictive modeling analytics? So in recent, like yesterday, all the data that we had and all the analysis that we did, that was something called descriptive analytics. Basically, looking into the past data and creating the report or creating a summary out of that. So when you are asking questions to the data and answers are coming out of looking at the past, like, what was my sales last year, or, what was the customer churn rate? Or these are all like looking in the past and seeing that, how it was like. So that is all descriptive analytics. Predictive modeling analytics is looking into the past, but predicting the future. So you are predicting something, you are not like summarizing something. So hey, last year this is all my data that talks about my previous year's sales performance. So what will be my future sales? I'm not asking like what was my average sales last year. I'm asking, this is sales data, tell me what might be my future sales, or how much I can predict to be my sales to happen, or what is the give me the prediction that how much data I will consume next month, what is the raw material I might need next year, or you're trying to do the analytics where you're trying to predict something for future. So that is predictive modeling analytics. Now there are a lot of ways to do that, but this is one of them. So you are just looking at the data. Basically, you are majorly working with your number and text data. NLP, you can still do NLP, but NLP is not generalized. When you say predictive modeling analytics, you don't talk about natural language processing recommendation engine, because this is not like looking at the past and telling the future. This is something very different when you talk about NLP. Now coming to NLP, NLP is natural language processing, speech, video, image processing. So right now, if you see all those as I was talking about language translation or language correction, language generation, image processing, computer vision, self-driving car. So this is also comes into natural language processing. Your video processing, you may see a lot of like, hey, this AI will can change the video and create certain videos, and machine generated videos, machine generated paintings and stuff like that. Speech, understanding your speech and like making the translation, and not only translation. So when you say something to Alexa, you can have different kind of tone in your voice. It picks up from your tone, understand what you're trying to say, and execute the whole thing. So that is also AI, like the capability of machine to understand what human is trying to say and make sense of it. And you can say any kind of sentence and it will understand what you're trying to say. And if it doesn't understand, it will ask you like, "Yo, can you rephrase what you're trying to say?" So all those things can happen. So all those areas where you deal with the like vision, speech, video, all these things, that is common in natural language processing. Recommendation engine, as you might know that when you open up your Amazon or maybe whatever website, they always have some kind of recommendation for you. So AI can also help understand who you are, who other people are, and kind of like build a recommendation for you, something that you might also like because you also did something else, or there are certain persona that you have and some other people have. And persona of you, like you are a college student, that is your persona, you are in a Surat, so probably you will be needing GTU based maths 2 book. So that is a recommendation generated based on understanding who you are. So that is also built by AI. So you can build this kind of system. Clustering is a problem where you have this bunch of data points and you want to basically cluster like categorize them, and you don't tell them what category they want to be. You just tell them, hey, this is the bunch of data. Now you guys figure out based on the pattern that what are the data points which are alike and what are not like. So clustering can be also useful in multiple ways when you're trying to like find out multiple patterns. So we will also look into that. So these are all very generic kind of applications of AI. In today's lecture, we'll be mainly focusing on predictive modeling, uh, because this is one of the most generic application at this point. We still see a lot of natural language processing also, that is like probably second level. But talking about industry and making money, predictive modeling is one of the things that people normally start with. And then you can go down the road. But the first thing that you would normally learn in data science and AI will be predictive modeling. It's a simple, it doesn't take too much data, ideally, and then you can see the result right away. And so predictive modeling is something that we're going to focus today. Okay. So what is machine learning model? So, you might be hearing like, we are building the model. So what exactly you are building when you have a data and you're building, some kind of AI model? What exactly model is? So just a classic definition from Wikipedia, that model can be thought of statistical assumption with certain property. So you're making some assumption with certain property, using certain property, and then that assumption allow us to calculate the probability of any event. So it tells you, so given a model is kind of a representation made through certain property and certain statistical assumptions. And with this particular representation, you are trying to predict the probability of future events based on those certain properties. In very simple term, what model is model is very generic term. And if you think about, let's say, a model of certain building, you go to some real estate builder, and they have like small model of their upcoming new fancy big building. So what that model basically is, it try to capture idea or try to capture the the whole real world assumption of that particular real world entity. So you have this real world phenomena, this building that is coming up, and you are trying to capture and represent in certain small mathematical small way. So you are building this small model which will be representation of what it will look like in real world. Similarly, in real world, all these like phenomena that, hey, there exists some pattern in the sales, like when you are doing the sales, so there is some pattern exists already. So can I make a model? My model will be a mathematical equations, and what I'm going to do is I'm going to use this data and try to figure out what this mathematical equation is, and this mathematical equation will tell me the future. So this mathematical equation will represent the whole event of my sales. So you have this sales pattern, or this sales phenomena, that you are doing your sales. There is a sales pattern in your how much sales you will make month by month, in past, in present, in future. And then what you want to do is you want to create some kind of equation which capture this whole trend of your sales, and you try to find this equation. And once you figure out this equation, so you can find this equation looking at the past data, and then you can use that equation to look to try to figure out what will be your future. Because now with using that particular mathematical equations, you are trying to like encapture the whole idea of your sales. Or in a similar way, let's say you are building a machine learning model for self-driving car. So your self-driving car model will try to capture that the whole real world idea, that what I should be looking at. I need to build something which can take input as an image and tell me what I should do as a next action. So you try to like encapture the idea of real world, what road look like, what a person look like, what a tree look like, what a sign look like. So all these ideas that you try to capture and then put into some kind of mathematical model or some other kind of representation, and then that particular representation you can use to predict the future. We will see a lot, but the idea what I'm trying to tell you here is a model is just try to encapsulate or capture certain ideas through mathematical equations, to some kind of tree structures, to some kind of neural network structure, and use that model, the way to model that has been built by looking at the past to predict what is the future look like. Now there are multiple categories in learning. So we talked about model. That means you're building the model. Now, what are different ways that you can build the model and what they actually are? So first thing is called supervised machine learning model. Now, supervised learning happens when you have certain data set where you tell that, hey, in this particular data set, this is the particular column that I want to predict. So let's take an example. Uh, let's say we have a data set of Titanic. Titanic is a very common data set. It has certain column called who survived. So you want to predict basically that, hey, I have all this information, who is the passenger is, what is his age look like, how much he paid for his money, in which part of the boat he was sitting at the time, and all these data points you have, and you want to say that I want to predict whether he died or not. Now, in machine learning model, basically we already have some tagged example. So you already have data that, hey, this is they are called training data set. Now training data set will have all these features or columns or data point, and then also we'll have an answer. So you feed all this data point and answer. I mean, what should be my prediction look like if this is the condition, this is my real world scenario, then what it will look like, and then you feed to the machine, and machine will learn from that. So that is for supervised learning. So basically, you are in supervised way. You are telling machine like, hey, when I have these values, then this is the prediction value. This is what I should predict. And so based on that, you have these multiple examples of what my different features or different columns value look like, and what will be the corresponding answers should look like. And now not all the answers are going to be same, so we will look later like how it look like. But the idea is you feed this all data set, and based on this examples, it will build a model using examples. Now there are multiple ways you can build this model in supervised machine learning. First is something called linear model. In the linear model, you have all this data, and you are trying to create an equation that your whole data set, or you can think your data as a an algebraic table, like row and column, a table, an algebraic table, that is your data. you feed this data to your model, and you're trying to build the equation. If you guys remember from your algebra class, you used to have this, like, hey, this is the matrix, now create the equation ax squared plus bx plus c, what it look like. So similarly, you try to figure out the equations. We'll see one by one in detail, but basically the idea is, in linear model, we are trying to, so our model is, and at the end we will have one equation, that is our output, that is our model. Our model is basically a mathematical equation, a linear equation, that is our model. That equation has been created by looking at the data. We will see how that will come to the picture. Now, second is tree-based model. In tree-based model, we have this like decision tree kind of thing, like literally a path, a graph, which is says like, hey, I start from here, so I go here, here. Now I had two more decisions to make. Go here, here. So there's like literally there will be a tree kind of structure. Uh, those who So tree structure, we will see how it look like, but it's basically a decision tree where you take one decision based on yes or no or certain answer. You go to second level, and then again you make certain decisions, and you create this kind of whole tree. And this tree is basically your model. So at the end, when you train your model, you end up with this tree, and using this tree, you will predict the future. A third way to build the model is probabilistic model. In the probabilistic model, your model is basically Bayesian probability equation. So if you remember the Bayesian property, where the Bayesian probability is basically uh, a dependency probability. Let's say if I have, what would be the probability of happening event A if B has happened? What is the probability of the occurrence of event A if B has already occurred? So that is the naive based probability equation, and that is what you end up with. Your model is basically the Bayesian probability equation. That is your model. Neural network, we will look into the neurons. Neural networks are inspired by the idea of our brain. Our brain has neuron, which is like basically it's kind of like mass like structure where there are like multiple neurons, and all neurons are connected with each other. So we can use that kind of so people thought that let's try to recreate the scenario and try to build a model which kind of replicate how our mind works, or how our brains has been wired. So that is the neural network. So that is how, so you end up with the model, the model that you end up with, which is basically a graph which has like multiple nodes with connected with each other. And we'll look into that, how they communicate with each other. But this is another way to make the model, that you end up with, your end model will be this kind of graph data structure. And finally, support vector machine. Support vector machine is basically a multi-dimensional mm, a vector. Basically, you end up with the support vector machine, you end up with the equations, but the equation is made very differently than linear model. So the way of building the model, support vector machine and linear model both will have a equation at the end, but the equation is made very differently when you are doing the linear modeling and when you are doing the support vector machine modeling. And support vector machines are basically known to work with the high dimensionality of data. When your data has so many, let's say there are like more than 1,000, 2,000, 3,000 column, and when you're trying to build something, so it's really time consuming, memory consuming to build this kind of model. And support vector machine normally do very well with this kind of data. So with the support vector machine also, you end up with certain equations, and how the equation is being made, we will look into that. So this is all supervised learning, where you are building this different, so you're building the model, and these models are built in different way, and all these models at the end are built using data that it has seen in the past. Through the example, it knows that, hey, if I'm building the model, I need to provide all this feature. We call it feature, we call it column, they are all same. What would be my output look like? And I give this example, I give multiple examples, and through that multiple example, looking at this multiple example and figuring out the probability of all these things, it kind of generate tree, or some kind of mathematical equation, or probability model, or some kind of neural network model, or all these kind of different things. It's really wild out there. Like, people have built the model with different ideas. These are the so far most famous model that you can see right now. Three are probably the most used and most sophisticated model. Like, it's a simple tree, but there are multiple sophisticated trees that you can build. But the idea is this is the normally how model look like in general. Now, unsupervised learning. Unsupervised learning, where you have this bunch of data point, you have data set, and you just tell them, hey, this is the data, now figure out within yourself. This is not supervised. You are not telling them, what my input look like, what my output look like. There is no concept of input and output. There is just concept of uh, a just bunch of data, and it will do its thing and try to like create some kind of cluster around it. Like looking at this data, at this point, this data point look like similar, and this data point look like different, and you can build a different kind of model. Now we will see one some small example to understand how it works and what the clusters are. But the idea is, in supervised learning, you teach them by example. In unsupervised learning, there is no teaching by example. You just throw the raw data, and then it will automatically build some kind of cluster there, some kind of similarity pattern there. Semi-supervised learning is where your parcel data is tagged. Parcel data is already like supervised, or you already know what the target look like, and parcel data doesn't know what it look like. So let's say, again, taking the example, let's say take the example of loan. So should I give the loan or not? And semi-supervised learning might have a data set where, while so we are trying to build the model, and the input to build this model would be half of the data will be tagged by example, saying that, hey, these are all the information about the user, and in the past, whether they have successfully repaid the loan or not. And then the half of the data will not have that idea. It will just have just the person's information, and it doesn't has the example from the past saying that, hey, for this person, whether he has taken the loan, whether he has paid the loan, something like that. So basically, semi-supervised is a mix of supervised, unsupervised. Half of the data is kind of supervised style, half of the data is semi-unsupervised style, and then you try to figure things out. Reinforcement learning is a different way of learning where you teach by example. Reinforcement learning also used a lot into games, and also self-driving cars. So basically, what you have is a model is basically, you give your model an optimization function, and you kind of like start training your model. So what happens, your model will try to, like, let's say we have tree model. So tree model, we have like some kind of so it try to form the first tree, and then it try to like run the tree and see the answer, and when it doesn't reach the answer, it like kind of, it has this one objective function. It's also called error function. You try to optimize the error function. So your tree will have different kind of like nuts and bolts, which different values, and you try to like set right value for all those nuts and bolts. Like, every node will have some kind of probability associated with them, and you try to figure out what that probability will look like. So we'll see how tree structure look like. And reinforcement learning, basically, you learn by an example. One of the very common example is I want to build a system, AI system, that can automatically land my car, or land my in the I want to have the uh, let's say I'm building the model for autopilot, and my model should not crash. Like, when I'm building this autopilot for my aeroplane should not crash. It should land properly without any, I mean, it should do it automatically without any human assistance. So you create the objective function that, I should not crash, and you do your mathematical way to represent that whole idea, and then you just keep simulating the whole thing. And every time you simulate, you tell them whether you crashed or not. If you crashed, then you change certain parameters value within your model, and then you redo it again. So you can look up reinforcement learning online, and you will see a couple of video example. But yeah, this is also one of those things. Now we will be major looking into supervised learning, because most of the AI problems, or the most of the AI is happening, or machine learning is happening, is around supervised learning. And supervised learning will also have categories of problems. Now, what are those problems? So as a supervised learning problems, what you're trying to predict, what you're basically trying to predict, that is one of the category. So regression problem tells you that if I'm trying to predict some kind of continuous variable. Now, what is continuous variable? Your salary could be continuous variable. Your weight could be continuous variable. Think about the chart where, like you're trying to predict what my future will look like, and that future question you're asking, the answer will be some kind of continuous variable. So maybe sales could be a good example. So this is a regression problem, basically, where the output variable, or the output, or the target that you're trying to predict will be some kind of numerical value, and that numerical value will be continuous value. So that is regression problem. Now, classification problem, when you say classification, it normally means binary classifications. And basically, you are building the model which will tell that given example in what category it should lie. So maybe let's say your AI system built for spam filtering, which can say, hey, whether this email is spam or not spam. So this is kind of like, this is the classification problem where the answer is binary, yes or no. Like whether giving this example, do you have diabetes or you don't have diabetes? Or given this example, is it an apple or an orange? So only there are only two ways. So you can see here, this is not in continuous value. This is just two possibility as an output for your model. So that is classification problem. Multi-class problem is basically when you say multi-class problem, instead of two categories, you have multiple categories. Now, why multi-class problem and category problem are very different? Basically, when you're building some kind of machine learning model, you normally, all the existing mechanism basically only provide you this classification problem, like, because at the end, what your model gonna give you, as we looked at this event, that the model basically calculates the probability of an event. So probability is like single value of the probability of certain event, right? So when you're trying to say classification problem, you have single probability, and it will have probability value that what is the probability of this event of happening, value between 0 to 1. And if it is more than 0.5, then you say A. If it's less than 0.5, then you say it's B. So basically, all the models are basically, their output is binary. I mean, like, only single value. And with single value, you can do only single classification. Multi-class problems are formed by something called one versus all. So they say that, hey, what is the probability of I have this like types of discount. I have types of discount. Let's say I have discount by email, I have discount by visiting mall itself, I have discount by a coupon, I have discount by third party partners. So I have multiple kind of discounts available for my customer. I want to see that what kind of discount would actually convert a potential customer into actual customer. Like what kind of discount if I give to certain user, so using that discount he will actually purchase something, right? So here what we're going to do, one versus all. Like what happens uh, if I give you email discount, and like email versus all, like if what it will, whether this customer will become, or will he become my customer if I give him email or I don't give him email. And then you go for like, what will he become customer if I give him like direct coupon through like physical mall where he's visiting mall. Should I give him coupon at the point, or should I not give it a one? So you for each of the category you do one versus all, and you build like multiple models, one versus all, and then you merge the result, and then finally you come to multi-class classification. Then you finally say that, hey, this has the highest probability among all of them, and this is my classification, or this is the class that I'm going to say that this is where it belongs. This is my output, that this particular user will belong to this particular class. You can say class because class is category, class are same thing. So so basically, multi-class is like you are doing classification problem again and again and again. So this is like a slightly different way to do that. It is not you just build one model and done with that. With multi-class, you build multiple models and then try to aggregate whole things and finally come up with the answer. So that's why classification and multi-class are different, because your model's output going to be just one probability value, and with that one probability value, you can just say yes and no based on your probability value, which always going to between 0 and 1. So you say that my probability value is 0.7. So I can say that, hey, 0.7 is more than 0.5. So my answer going to be B. Or, hey, my the model output, let's say 0.376. So 0.376 is less than 0.5. So my answer going to be A. So that is how you say that A or B based on like, you have this one cutoff which says that after this cutoff is going to be A, or before this cutoff is going to be B. So something like that. So that is why model can only do classification, and that is why you need to like do one versus all for all the available categories for doing multi-class. Let's say category of disease. This is also one example. What is the category of disease if these are all the symptoms? Does it look like diabetes? Does it look like heart stroke, possible heart stroke? Does it look like, let's say, cancer? Does it look like brain tumor? So all this category you have. So you basically build multiple models in classification, one versus all, and finally come up with the answer that, hey, for this particular user, it looks like it's a brain tumor. So something like that. So that's why it's a different category, because the process itself is different. Now, time series problem. time series problem is also kind of again we are forecasting something, and it's a time aware modeling. So basically when we are looking at the regression problem, and when you're talking about I'm going to predict someone's salary, someone's weight, a person's weight, a person's salary, then you're not this is not like a time aware modeling. Basically you have this set of data, then there doesn't has to be time tagged, there doesn't has to have a column which says time, and I can just do the predictions because it doesn't matter, because the nature of the data itself that there is nothing to do with the time. It doesn't matter what time the data comes from, as long as the data that I'm collecting for user. Let's say I have a user for whom I want to predict that, uh, mm, or not user. Let's say sales is a very good example. Let's say in the sales example, I want to predict what my sales will look like in future. So this is very much pattern. This pattern is time sensitive because the sales will be different at different time. If you're selling ice cream, the sales will be different when there is a summer, and sales will be different when there is a winter, and sales will be different when there is a, let's say 2013 has a good trend of ice cream. 2014 people move from ice cream to, let's say, uh, 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 more like a smoothie or juice. And then, like there are different trends which are changing over the time, and they're always going up and down. So let's say your stock market, well, company always like, hey, company is doing very good, then it do bad and it do good. It's not like the stock price of the company will never be linear. It will be always like going up and down and changing with different seasons. So the examples of sales or examples of the stock market value, they are all time sensitive because the pattern itself is a time sensitive. So what basically model is basically pattern, and these patterns are basically time sensitive. So when you have time sensitive problem, regression problem, you go for time series. Now what is different between time series modeling and regression modeling? So in the regression problem, when you're trying to teach model with an example, uh, you can just shuffle the data and you don't really care about how the data is being fed into the model. So I can just throw a bunch of data, and based on linear or tree, it will try to build the model. It doesn't look at the time. It doesn't. I don't have to be worried about the first data that I'm feeding to it. Will it is it like the data coming before or after? So let's say give you again, like to make it more clear. Let's say if I'm building a regression model, I can feed the data which was today's, which was captured today, and then on the next line I can give the machine data that was captured, let's say few days back. So because it's a machine, we are building the machine, we are row by row, we are feeding data one by one. So when you're feeding the data, you don't really care about the data's timestamp or data's timeline. So the row that you are feeding at the particular point, let's say that data was produced today, and then after down the line, the 10th row that you are feeding the problem, your model too could be, let's say, a month older data. You're not respecting the time in which the data was produced. You're just randomly giving the data and feeding the model. You're not worrying about at what time. In time series model, you need to be careful about how you feed the data. Your data that you feed to the model will be in the manner of time sensitive. So that means when you're building the model, you will be feeding the data of day one as a first data point. Then the next data point that you feed to the model will be of second day, of third day, of fourth day, fifth day, likewise. So it will be sorted by the time, and data will be feeded in the certain time wise. And again, because this is time series problem, is capture the real world phenomena which is time sensitive. So it requires some of the sophisticated model. There are some model like aroma, and there are a couple of other models out there. Time series is a huge topic, but what I'm trying to say is time series is out there, is different than regression problems. It has some similarity in terms of at the end you are looking for that continuous variable, like your the value of particular sales will be a numerical value, a number which says that I'll be making, let's say, 1 lakh worth of sales at that this particular day. So this is numerical value. But when you're building the model, it's a time sensitive data is being fed in a linear way with the timestamp sorted way, and that is how it kind of like pick the pattern, like, hey, today was this, that, this, that, and kind of like build the whole timeline chart. So with time series problem, you see timeline chart. With the regression, there is no timeline chart because there is no time. It can be it can be in any pattern, and you can just fit the data. So based on the problem that you're tackling to, is your use case time sensitive or not time sensitive, you can choose any of them, regression or time series. Both of them will predict the uh, numerical value. Your time series cannot be classification value. Time series cannot be multi-class value. Because as a nature of time series, it is just a special case of regression problem where your regression problem is time sensitive. So certain things has to be extra taken care of for this special use case. So this is the main 4 categories supervised learning, where you build the model by example, and these are the basically category of problems. For the regression problem, you tell them this is a person, this is his salary, this is the second person, his salary, third person, his salary, and then you say that this is all my data point, a person's data, and this is what I'm going to target as a salary column. And basically, model will take the training data and then split your data into this n minus one column and that one column, and then do the whole thing. And classification is again the same thing. You tell them this is the data point and this is my target. My target, let's say, is the disease or no disease. So I tell them this is the person. Did it has a disease? This is the person. Did it have disease or no disease? And then based on that, learn from that. And final time series, which is same as supervisor regression problem. So we are talking. I've been talking about this, like this n minus one column and final column that you want to predict. So what it looked like. So there is very good term which is called dependent and independent variable. So let's look at this example. This example tells that we are trying to build the model which will suggest us whether we should go and play or not, or whether someone went to play outside or not. Play is just went to play outside the park or garden or something like that. Now, what are the categories? What are the parameters on which? What are the features or what are the columns based on which you finally decide? So your outlook, your temperature, your humidity, your windy. These are all independent variable, and this is your dependent variable. This is dependent because value of this particular variable is dependent by all these four other columns or 4 other features. So these are all independent variable. It has independent value, and this dependent variable, its value, play or don't play, is associated with or is attached with all these other independent variable. And normally, this dependent variable is what we are trying to guess. So let's say if I want to build the model, I will build the model where I will fit the example. I will tell that, hey, tree-based model, this is my feature look like. All this like outlook, temperature, humidity, and windy. These are all my independent variable, and this is my dependent variable. So model will try to build itself and try to create that model itself, which will in future will take only this 1, 2, 3, 4 this independent variable as an input and try to predict this dependent variable. So when you feed them in supervised learning, when you feed them, you give them all this independent variable and ask them to build the model. And this is the example that if these are all the values, then this is how the dependent or target or my final results should look like. So I'm teaching my model like when it's sunny, when temperature is 25, when it's humidity 85, when it's windy and windy is low, there's weak wind, then I should play. So I'm giving the example like this is in this condition I'll be playing. And then this is if it's raining, temperature is really low, 15 degree, humidity is really high, wind is very strong, then I should not go to play. So this is the example. This is supervised learning where I'm teaching by example. Learn from this example, take all this and think that if this kind of condition occurs, then I'm going to play. This kind of condition occurs, I'm not going to play. And then you give them all kind of. Now there might be some example which says that it's a sunny, temperature is 25, humidity is let's say 80, and windy is weak, and I don't want to play. So it's not like every example going to be unique. There'll be a lot of repetition. There'll be a lot of repetition or small changes in one or the other parameter compared to different rows. And so basically it's a probabilistic decision. This is not so when your model being built, it basically plays around with the probability. So when you say that, hey, I have a lot of example which says that a lot of sunny. So let's say 10% is sunny, 10% of my example is sunny, and temperature is 25 and 85 week, and I have decision which says play or not play. So I'm going to build some kind of probability around it, that what should I do, play or not, based on all. I'm going to build some kind of probabilistic model. Every model will have some kind of probability attached with them, and based on that you decide basically. But the idea is supervisory learning, independent variable, you use them to do the dependent to predict the dependent variable, and we are training data while you building the model. You'll be providing all this thing and tell that, hey, this is the dependent variable. Now build the model. Once the model is being built, when it is ready to make predictions, of course you won't be providing decision because this is something you want to guess, or this is something you want to predict. So once your model is being built, you pass this outlook, temperature, humidity, windy, and then ask model that, hey model, tell me, should I go out and play or not? So this is supervised. This is training phase. In the training phase, you provide dependent variable, and in the testing or in the actual, once the model is being built, because you don't know this data, you want to know this value, and then you pass this value, and because it has learned from the past, it has learned from the pattern, it has built certain equations, certain brain style model, certain graph model, certain tree model. So based on that, it will finally give you answer play or not. So this is supervised learning is dependent independent variable that we normally talk about. Now let's talk about data types. Now, when you're building the model, the type of data also matters. So basically, you're gonna, if it's a, we are, as I told you that we are looking into predictive modeling analytics. We'll be not dealing with speech data and other kind of data. We'll be basically dealing with pure number data. Number and categorical means text data, and text is not more like a text, more like a category. So here you will see. So numeric data, there could be two kind of continuous and discrete. Continuous, where there could be infinite values like weight. It could be 0.10001, or like let's say 56.775, 59.665. So your model need to know that you're feeding certain data, and that data is in the space of infinite, like it's a continuous data basically, and it could have infinite number of values there. The range could be, you can say that the range of the data could be 10 to 20, but within just 10 to 20 you can have infinite numbers, right? That is your continuous data. Discrete is finite. So when you say like age your discrete data, because of course like you're going to have range between, let's say 0 to 120. I don't know anyone can live more than 120, but that is going to be finite numbers. You just have 0 to 120. There's no floating point going around here. The idea is that it's going to be finite. So these are two basic category of your numerical data: continuous and discrete. Now, categorical data. Categorical means some kind of category, male, female, or let's say blood sugar, low, medium, high. So these are all categorical data. Now, categorical data has two categories basically. Now your machine learning model has to know all these things. You also know all these things because you are trying to teach the model. So, when you're trying to teach the model, you need to tell them what all these different nuances are. So that's how it can understand how to learn them and how to see them. So ordinal model, it has some kind of hierarchy. So let's say low, medium, high. So you can see there's some kind of hierarchy going on there. The low comes first, medium comes next, high comes later. And there are a lot of examples where you can see this kind of like low, medium, high, or some kind of hierarchy going on in your data set. Let's say 1, 2, 3. That is also a hierarchy. Let's say let's say a job role. Let's say junior engineer, senior engineer, and manager. So there's some hierarchy. So when you have this kind of data which represents some kind of hierarchy, it's called ordinal data, and you have to like treat it likewise. Then there is something called nominal, where there is no hierarchy, like male and female. There is no hierarchy going on here. So this is nominal data in your categorical type of the data. So just mindful of those things, because we'll be using these kind of things. Now let's talk about different kind of models. So first thing is linear model. So what is linear model? Linear model, when you're building some kind of linear model, you have these different data points, and you kind of like so let's say we only have two columns. So you have 2D data, and these are all these dots are basically like X and Y values of the data. And what you're trying to do is you're trying to uh, build an equation which satisfied all these data points. So what does it mean? So let's say I have like 5 data points, and if I can create a line which pass through all these 5 data, then I can think that the next data that will in future, I can predict the value using Y. So let's say this is like your X, this is your Y, and this is my like let's say independent, this is my dependent values. So if I can create an equation where I can pass the value of X, and it will tell me value of Y, so down the line I can predict the future. So this could be multidimensional. And if you look at the equation here, ax plus bx squared plus cx cube, so basically at the end your model will learn the value of A, B, and C. So that is what, when you're trying to fit the data, it will try to build the equations, and inside that equation it will try to figure out what is the value of A, B, and C look like. So once you have A, B, and C figured out, then you can say that so while learning the data, you provide what is my Y look like and what is my X look like, and then you say you end up with some kind of equation which is made of A, B, and C, and you have like every row will create an equation because your x, so your y is your decision, as I told you. Let's say this is an example. So my decision is my y, and this is my x. Uh, you know, uh, uh, this is all my x, and when I'm trying to build the model, so I pass my value of x and I pass my value of y, I end up with equation which has only A, B, and C. So during the training phase, I end up with all these A, B, and C, and finally I try to figure out what is the value of A, B, and C through series of equation, one equation for each row. So that is how I will come to figure out the value of A, B, and C. And in the future, when I will have value of X and I will not value of Y, but during the training phase, now what I already have figured out what value of A, B, and C. Now I will have value of X, different value of X through here, and then I can figure out value of Y. So Y is your target. You can say target category, target variable that you are trying to predict. And using this equation, yeah. So you first figure out this equation, like what my equation will look like. Then for the new data set, you fit the value of X and you try to get the value of Y. So this is how you build the model. This is your mathematical model, and this is how you first build the model by figuring out this equation. And once you figure out this equation based on your input data, you finally end up with the equation where in future when you don't have value of y, which is like your testing phase, you want to figure out what is the value of y, and you can just pass the value of x, which is coming out of this independent variables, and you will finally get value of y, which is basically your dependent value. And if it is a categorical problem, so your y would be a probability between 0 to 1, and if it's a regression problem, it will be some kind of like some like salary, like some kind of random, let's say 35,000 or some kind of number. So based on categorical or numerical, the value of y will change. So this is how your model look like. This is your linear model look like. So this what this equation is basically doing. So visually, when we see the data, this is your data point. This is your y. This is your x. So in the x, so basically this is our example that you already put out there using this is your x and this is your y. This all make your x and this one make your y. So you throw out there. So you end up with this all this data point, and now you're trying to build the equation. That equation will try to satisfy as much data point as possible, ideally. So you may not you may not able to find the equation which satisfy all the data points, and when you're not able to fit all the data points, that is when you say that your probabilities, your model's probability is not 100%, because it's a training probability. So basically it says that your model was trying to fit you are trying to fit the line in all this data point. So this is all known data. So when you able to fit the line, or whatever line that you end up fitting with will be your equation. So once you have fit the line, so you know what line look like, what the pattern look like. So when you provide some random value in the future of x, you will know based on line, hey, if my value of x is here, so I can look up at the line and I say that, hey, my value will be here. Or let's say I have some data point here, unseen data that comes here. This is my value of x. So I can go up and I can say that, hey, this is what my y value should be, because now I have this line, and based on this line, I can tell that what would be my y value with. So this is how you build a linear model, and this is how basically the line that you end up with, which is basically your model you end up with. And when you pass the value of x, it will just solve this equation, tell you y, and that is your answer. So this is how your machine learning linear model look like. Now let's come to tree-based model. In the tree-based model, it basically creates some kind of decision tree based on the different category. So this was a categorical example, play and don't play. So I'm gonna show you the tree-based model which plays around with this. So you can see that there's the outlook, temperature, humidity, wind. These are like 4 independent variable, and this one is a dependent variable. So what you do? So basically, you look at the example. Like let's say you have 15 example of play and don't play. So you start with outlook. So my first column gonna be outlook. Now what outlook has? Outlook has sunny, windy. Let's say sunny and rain. So for sunny and rain, and then let's say there is one more overcast. So I look at the example, like out of all the examples, sunny, overcast, and rain, how many examples are sunny says that I should play and don't play? How many examples overcast say that I should play and don't play? How many rain will say that I should play and don't play? And based on this value, I'm going to set up some kind of probability here that when data comes in, with this particular probability, I will go to here. This particular probability, I will go to there, and this particular probability. So based on certain probabilistic value, you choose on which branch to go to. So now let's say you choose sunny. So once you choose sunny, then you want to figure out, what would be my humidity look like? Should I play or don't play? So you kind of create the decision tree based on the data, and you kind of put some kind of decision values out there. So based on this particular probability, you choose certain branch. If your probability is like absolute value, then it's a like perfect decision tree. There is no, but that will not happen for the reason that you will see a lot of example which are counterintuitive. So let's say you have a data set which is uh, uh, let's say a data set coming out of Moscow and data set coming out of India. The Moscow is very cold country and India is very like humid and country like that. You don't know those certain values, and you might have same values of, let's say it's a Moscow, but you can't really go out and play in sunny and like sunny and very good humid. There could be some other reason why you can't go out and play. While in India, so you can see a lot of contradictory examples also. Not all the examples that you fit to the model will be like perfect makes sense example. There'll be a lot of like, hey, I have these two values coming into my data set. One, for both of them, my input value look like exactly same. My all independent values are exactly same, but my output look like different. So I might have like same row somewhere down the line with all these values same, but we'll have different decision. And like, hey, I saw the example which says play, and now you're giving me the same example and you are saying that don't play. What should I do? It's counterintuitive. So what happens, you basically figure out, hey, for very very same data set, how many data set which is sunny, temperature same, humidity same, and weak says play, and how many data set which is sunny, temperature 25, humidity 85, windy, and say don't play. So within the same data set, I have like two set of data going on, and then I can set probability. Like for the same input data, I have seen that with, let's say, out of 10 data, 7 times it was say play and 3 times it say don't play. Counterintuitive example, 7 times say play, 3 times say don't play. So I can set the probability as 0.7, that when I see this example, I would say play or don't play by probability of 0.7%. So this is how you set the probability, and this is how we keep setting probability on the each level, and finally you end up with the tree which has like all this kind of like all different branch based on different your dependent values with certain probability. And when certain data comes in, it says that, hey, it's an outlook with a probability of 0.7, and with the probability of 0.7 should I tell them to go sunny, with the probability of 0.7 should I go uh, overcast, or I go with the rain, and likewise. So you create you create the tree with all the dependent variable branching off with certain probability. That is a tree based model. So you see that this is very different than linear model. But at the end, so here what will happen at the end, when you come all the way down to the tree, it will tell you that whether you should play or not with certain probability. Here you end up with the y value. So using so these are the model basically, which are really designed in different way for the same final objective, but really choosing a different outlook. So your model here is basically mathematical equation, and your model here is basically some kind of decision tree. So now let's look at the probabilistic model. The probabilistic model is basically categorical model where your y is dependent on multiple x. So in this example, your y was play or don't play, and your x is basically all this humidity, outlook, windy, all these things. So it is just basically a probabilistic equation that when what my y should look like given given the value x1, certain value x1, certain value x2. You can look up naive based classifier, or naive or naive wise conditional probability equation, which says that like probability of a given b equal to probability of a into probability of b divided by probability of b given a, and something like that. So it creates the whole probability equation around it, and based on that probability equation, it basically try to create this kind of model where every link will have some probability associated with them. And basically within that, so you end up with the model which is basically this kind of probability equation, conditional probability equation. Based on that, you say that whether I should go with the y or not. So this is one more way to create the model. This is not tree, this is not decision tree, this is more like a probability branch out, and there's only one link, there's no like whole tree structure. This is just y and directly connected with all the x. So this is one more way to create the probability model. Now neural net.
Don't get scared. This looks scary, but really when we go down, it's like not that difficult. I'm taking a lot of time here because this is like the biggest part of the whole thing. We'll learn things faster going forward. I need to keep my eyes on the time. So what does neural net look like? Neural net is basically inspired by the idea of our brain. So in our brain, if you have seen certain movies where they say like inside the brain there are like all these neurons which are like connected to each other and they're like sparkling, spark. You can see like if you see some sci-fi movie, they're looking into brain or something like that. So this is something like that. So basically, neural network has these neurons represented by the single node. Now what this single node has, so it takes input as an x. uh, there is some weight associated with that, with the connection, and then there is something called activation function. So what activation function is basically, so when I make some kind of input, so this node will take a lot of inputs from different neurons, and based on that input, it will have something called activation function. As it is a function, so this function will have like these are all input to the function, and output of the function will be some kind of probability or some kind of value. And then my activation function will tell me, should I pass on this value to the next or not? So that is your spark you see in the movies, like spark. So there will be some kind of threshold, which is called activation threshold. Understand, it's called activation function. So basically data is coming in, this is doing some mathematical work, it is coming out with some output. This output is certain number, and I have this mathematical equation which tells me that should I pass on this data to next or not. So you have this multiple node which are interconnected with each other. This is layer one and this is layer two. So if you see that these layers are not like mesh structure, this is like some kind of uh, uh, directed acyclic graph. If you understand this term, directed, there is a direction here. Acyclic, there's no cycle going on here, and there's a graph. So it's a graph, like a mathematical graph. So input, there is no cycle, and then there's like direction here. So all this node will have all this data coming in from different nodes. It has this function which takes all this as an input, it compute the value as an output, and based on the output it will tell that whether I should go or not. And when you say that I should pass this value, so what value it will pass? It will pass the value that it has been calculated. So it will, so either it will be 0 or it will be greater than 0.5. Like, let's say this node at the value 0.7, and my activation function says that if it's more than 0.5, then I should let it pass. So this will basically spark and pass the 0.7 value going forward. Let's say this one came up with 0.3 value. Now this is zero point 0.3, and my activation function says that, hey, I should not activate this thing, because this whole mathematical equation telling me that the function's output value is 0.3, and my activation function says that, hey, zero point 0.3 I haven't met, I should not activate. So even though there's 0.3 going on here, I'm gonna pass 0, means I won't pass anything here. So when you are activated, you pass actual value. When you're not activated, you don't pass anything. So this is how this whole thing look like. Now your x1, x2, x3, x5, these are your independent variable. Those temperature and humidity and those kind of thing. So that you pass on here, and then it comes here, and based on the value, it will be whether activate or not. Now there is the weight associated with each of them, and there are different value of weights, and and this different weight will have different. So this weight is associated with the link with different neurons. So there's a different weight from, so node 1 to node 1, node 1 to node 2, node 1 to node 3, node 1 to node 4. So like in kind of cross multiplication, this all link exists and weight exists. And when you pass on some values, it will be multiplied by this weight, and then will be passed on to here. And this is something called hidden layer. And finally output. Now what happens when you're trying to train the model? Basically, when you train the model, you're basically setting up or trying to find the value of these weights. So when you are trying to train the model, you start with the random weights. You provide all the x. At the end, you will come out with an output, like input multiplied by weight coming to all this second layer. Second layer will take all this output, compute the function, activate or not. If not activate, finally all this will come to the final node, and this will come out as our output. Now at the output point, I will compare with the value of y, that is I already know. This is a supervised, so I know y, what y look like. So I will compare with y that has been created by the model, and y that I already know. I compare, I see that, hey, there's an error, and then I do something called back propagate. So I pass that error that, hey, you you were off, the actual value was, let's say, 0.75, but you came up with 0.66, so there is a difference, and I will pass this difference, and based on that difference, all this weight will be reset, or will be like kind of set, or kind of changed, or kind of tweeted. So back propagation. So now you are tweaking your weights, and now your weights will more aligned to what it looked like. Again, you pass the data, it comes out, it compare with your result, and then it back propagate error and try to fix the weight. And at some point, all this weight value will be adjusted certain probability. Like the weight will be like let's say this started with the 1, all of them started with the 1, and at the end of the model, when you see that the error is very less, all this weight will be something random, like this weight was end up with 0.71, this weight end up with 0.001. So your final neural network model look like what it looked like when it's finally being trained. It is a model. So structure is, so here you define the structure automatically. So here your structure was predefined. Here your structure is not predefined. It creates model on the fly. It creates tree on the fly. Here it creates the equation on the fly. You don't tell them how many these terms I need in this equation. So the model will create the term in its fly. Here you tell them this is my structure look like. This is how all my weights are. This is all my activation function. All you have to do is train the model. So as a result of training, I will be end up with these different weights. So my input is data, and input is this structure that I define, and then my finally when the model is being trained, basically is my finally trained model is a modified model which has its weights being adjusted for my predictions or for my value. So this is how neural network looks like.
What ठीक है?
Madam, can you mute? Anyways, so this is how your neural network model look like, and when you are training the neural network, this is your hidden layer. Now, when you say deep neural network or deep learning is basically same thing. It uses the same structure, but here you see this is like your input layer, this is your output layer, and then there is hidden layer. Now, what happens in deep learning? Why it is called deep learning? Because you have this multiple hidden layers. So this is layer 1, then there will be layer 2, there will be layer 3, and there will be multiple weights and multiple activation functions. So let's say copy of like the same layer 1. Let's say you have like 2 hidden layers. So this is layer 1. You're going to have very similar layer here also, where all this input will be connected with all the output of my second hidden layer, and then you can go like however you want. So you can have like layer 1, layer 2, layer 3, layer 4, however layer you want to create, you can create, and then you give the data to like finally fix the weights, and that is your output. So deep learning, why it's called deep? It's called deep because of all these hidden layers. So the meaning of deep comes from this multiple layers that goes in between the input and output layer. That is why it's called deep learning, because of these multiple layers. And basically final structure will look like this kind of the weight being set for the tree. And then so this is like very simple directed acyclic graph neural network. People have come up with different kind of structure, different kind of like there's so much optimization, so much customization in this very basic structure that you see nowadays. But for like very essential, for a very basic, like 1950s first neural network proposal will look like this, and then today state of the art will look like much more complex. But the basic idea is this is what the basic idea of a neural network or deep learning. You have weights, you have nodes, you have activation function, there are links connected to different layers, and there is no like there's always link connected one layer to other layer. There is no interconnection going on within the layer, and then by example it learns. This is your neural network. Let's say reinforcement learning. What happens in reinforcement learning? So reinforcement learning, you see that all these Tesla self-driving car and stuff like that, who are testing for whether it should like stop, whether it should drive, whether it should crash, all the decisions that come out this final layer. How it does, it provides all this input data from real life. It comes as an output, and it check whether I crashed or not. If I didn't crash, then okay, I'm good. If I crashed, then I'll go back and twist my layer. And then, so here my output is not Y. I don't have this Y reason. I have this optimization function. And my optimization function says that, did I end up being crashed or not at the end? So if I provide all this input, did I crash or not? And now I don't have answer, basically. I simulate the whole thing. So with this input, I don't know the answer. I just give this input. I simulate the whole thing. I will see after the simulation whether I crashed or not, and then I tell my model, hey, with this I crashed, so go back and fix certain things and run the simulator again, and then you keep on running the simulator. Your optimization function is like crashed or not, or some other variable, or let's say speed, or it could be anything. It's a very complex problem, but the idea is this is how reinforcement learning works. That you give the data, you see the output, you see whether you crashed or not based on, or whether you see how much error far you have in the optimization function, and then you go back. Instead of why, you have optimization function to guide you through your trading. Basically, that is reinforcement learning. You don't train by example, you train by simulation. Basically, that is your reinforcement learning. Okay. Now, this is the last kind of model, support vector machine. Now, what support vector machine is? So you have something called, you trying to find something called hyperplane. So imagine that you have this multi-dimensional data. So right now you can see two-dimensional data here, and then you're trying to pass this one-dimension line here. Your line is one dimension here because it only has x, and then you have like x and y two-dimension here, and this is like plane and this is line. So line is one dimension, plane is two dimension, and then you can go three dimension, four dimension, five dimension. Three dimension is cube, and then if you are capable of thinking more the mathematical terms, you can have n dimensions basically. So anyways, so you have these two category 1 and category 2. So what you're trying to do is you are trying to find that this divider line which will within that two-dimensional plane or three-dimensional plane or n-dimensional plane, you're trying to find this particular line or this hyperplane which will divide your two examples. So let's say there are two categories, category 1, category 2. So this tells you that let's say did he defaulted in his loan or not? Defaulted means repaid his loan or not. So let's say these are all examples we say didn't pay the loan. These are the examples that all of them paid the loan, and these points are being thrown out based on that. So let's say you have a person who has five categories, five features. So with five features, you can create the five-dimension plane, and you can point this dot there based on those five dimensions, like five feature point. So multi-dimension based on multiple features, you can create for the number of features, you create multiple dimensions. Like if you have two features, two dimensions, three features, three dimensions, you end up with this kind of plane. And then based on this plane is basically going to be your final y or a final equation, which will tell you the y, whether it should be divided or not. So in the support vector machine, what you're trying to do, you're trying to find this divided line, and you're trying to find this best margin. So I can like twist my line like up and right and left, and so you can imagine that. Let's say if I'm like rotating this line, if I rotate this line, my distance of this line with all this example will either be, it will go some closer to some of them and far to some of them. So what I'm going to do is I'm going to calculate the error or calculate the difference with distance between my line to all these other dots, nearby dots, and based on these dots, I'm gonna I'm gonna calculate the error here, like how far away I am or how many mistakes did I made in this thing. So now you say that okay, so this line is only looking at it nearby nearby this margin. So what does this margins look like? So these margins are actually support. So when you say support vector machine, the keyword support comes from this margin line that you pick it up. So this margin is basically support for this line, and vector is basically vector, and support vector machine. So basically this is the vector that you are trying to find, and this only work. So one more thing, that this only work with the numerical data, because as you see here, it is all about playing with the multi-dimension data. So it's a dimension, it's a numerical thing. Dimension 1, 2, 3 is a numerical representation. So if you have a data which had text or category, this will not work. It has to be numerical. So basically, support vector machine, you are trying to find this plane which divide everything. You have something called margin, which is basically support, and based on this line, you are trying to calculate the error, and you are trying to create this lane which has minimum error. So at the end, it's an optimization problem. So basically, you are trying to create this equation of this plane which has least amount of error. And how your error is defined? Your error is defined by all this within your support. How many nodes are there, and how many you are close and far from these examples. So this is basically your support vector machine. So one thing I want to reiterate over every example, whether it will work with the number or not. So this will not work with the text data. If you have text column, you have to convert them into numbers some way. There are multiple ways, how you represent a category into numbers. We'll look into that. So support vector machine, all the input has to be in the form of numbers. It doesn't work with the categories. Neural network also only work with the numbers. As you see, it's all about number and mathematical numeric equation. There is no category. Probabilistic model, this can work with number as well as category, because it's a probability. So you're basically telling that, like give by example, you're calculating probability of occurring A versus B. So this can basically, this is not like you're not performing any, adding the numbers or deleting the numbers, or optimizing the numbers. You are just doing the counts on things, because categories probability is basically count, like how many times it occurred out of full examples. So it's all playing with the frequency of the certain things. So this will support, so you can directly feed a number and categorical kind of data into your model. You don't need to pre-process them. Tree can also do that. Tree can also work with the number as well as uh, text-based or category, numerical and categorical variable. So I'm going to call numerical categorical variable. So that will be, when I say numerical variable, this is what I'm talking about. When I say categorical variable, this is what I talk about. So linear model will only support a numerical variable. If you have categorical variable, you have to convert them into numerical variable. And we'll see there are some techniques to do that. Tree-based can work with numerical and categorical. You don't need to specifically do the conversion. So you can do that, you cannot do that, it's optional. But if you don't do that, it will still work. It will not fail. This will fail if you supply categorical variable. It will just say that, hey, I don't understand this data, I can't do linear model with this data, there is some text going on here, I don't understand text. This will do with that, I can understand text, I can build the model. This will say that I can understand text, I can build the model. This will again fail, hey, I don't understand text, I cannot build the model. So just like to mindful. And support vector machine also says that I can deal with the numbers, I cannot deal with the categorical. So with all this thing, you assume that, hey, it's a good idea that whenever I get some kind of categorical data, I should just right away convert them into numerical data and finally create the final data set that I'm going to feed to my model, which will have all the numerical data. There is no categorical data going on there, because a lot of my models will not support categorical data. And finally, unsupervised learning. So unsupervised learning, as I told you, that you just throw data into the space, and then you try to figure out different patterns or different clusters among the data. So let's say you are throwing out the data in 2 dimensions, and then you define something on centroids. Centroids are basically like, this is some, I want to see the cluster around this one, I want to see the cluster around this one, I want to see cluster on this one. So I have chosen 1, 2, 3, 4 centroid, and then I'm going to increase my circle, or I'm going to calculate the distance of every node, which is basically I'm gonna calculate distance of every node with every centroid, and with whoever it is closed, it will end up in that particular cluster. So let's say I take this particular node, I will calculate the difference or distance of this. Distance is you can say Euclidean distance, right? Because total numerical thing. So you can have like x comma y comma z, x comma y comma z. Now calculate the distance between these two, these two tuples, or these two variables, or these two vectors. So basically, this is the variable which is represented by x comma y, and then these are the centroids, and these are also represented by x comma y. And I'm going to calculate what is my difference look like, Euclidean distance look like from this point to this point, this point to this point, this point to this point, and this point to this point. So I will see that this point has the minimum distance with this particular centroid. So this will be part of this become part of the cluster, and this cluster, and the cluster which is defined by this particular centroid. So every cluster will have this one centroid. And so if you see here, I'm not, there is no example going on here. You're just, there is no like that one particular target column I'm thinking about. I'm just clustering data. I'm just throwing out the data, seeing what is the difference look like, and try to find a pattern. And then whoever has the, and whoever like close to each other, which is like the pattern here, I'm going to create the cluster here. In all this example, there was one guiding idea that here you say that, like, here's the example which says that this is my cluster 1, cluster 2 classification. This is like, there's this y column, and try to compare everything with the y. I'm trying to compare everything with the y. I'm trying to compare everything with the y. So there's this one y going on in supervised learning. In unsupervised learning, there is no concept of y. It's just all x or all data, and you just like try to build. So this is why it is unsupervised learning. You don't teach by example. You just throw data out there. There are different techniques, so we'll like try to cluster data together. I have slightly more time today. Please stay with me. We will definitely go more than 2 hours today, I'm sure, because we are still here and we have a lot to cover. So I have my next meeting around at 11. So till 11, I'm going to be around. So, please bear with me and understand this is worthwhile. What I'm teaching you right now, it is like really crash course. When you will enter your, machine learning AI class, wherever in whatever semester, you will be like, I know all this shit. Okay. Now let's talk about something called the idea of underfitting and overfitting. Now, what is underfitting and overfitting? So as you see there, you are trying to learn by an example, and you are trying to learn by example by looking at data that you already know. But when you will be finally testing your testing your model or try to see how much good your model is, you will be applying the data which you have not seen before, right? You build the model with seen data, you build the model which where you already know the answer, but then you're going to predict on the data that you have not seen before. Now what happens sometimes, with the data that you have seen, you try to like over optimize your model. You try to build the model, let's say in the case of regression, you try to build this line which is like super optimized, and that means that next time it is like so much optimized into existing pattern that it's overlearn the patterns, and when something new example comes in that doesn't meet the pattern, it will just say that, hey, like it will not like give the proper value because your model has been overfitted. Sorry, this is the example overfitted. So if you see here, like, your model is like trying to crazily, so this is something look like the actual example. So this is, let's say, my actual, or this is like the green line here is the real world scenario. This red line is the model that I have built here. Let's start from here. So green line is the actual scenario, the red is something that I have done. So here what I'm doing here I'll start overfitting. So here with what I did, I built the model which was like very overfitted. So overfitted means I built this complex model which was like 100% accuracy in my testing data. I'm touching each and every data point, and I'm creating this mathematical equation that will satisfy each and every point. There is no error going on here. So what happens? You end up with this kind of very complex linear model. This linear model or this line represent this complex linear model. And when you compare this the model that you built with the actual real world scenario, which is this green line, it is far off. Like, you're doing so many mistakes here. You're far off. Like, okay, it is doing good here, but like it is all this point, all this point, all this point. See the difference here. Huge difference here, huge difference here, huge difference here, huge difference here. So you kind of overly optimize your model, and now it is far from original scenario because you don't know the original scenario, right? You are building the model by looking at the example. So with looking at very, like this is your actual real world, like this continuous curve, and you just know when you're training the model, you are just training your model with this particular like small these dots are just the like dot are your selected data points using which you are actually building your model. You are trying to train the model using this dot. You are trying to learn this green curve, but because you're trying to over optimize on all this dot and going over all this dot, ideally you should be close to this green line, but now you're far off this green line and you are much more distorted. So this is the idea of overfitting. So that's when you say that we are trying to build the model, and when you try to like test the accuracy of your model on training data, and it says that, hey, my accuracy is 100%, then you are actually doing a lot of wrong because you're far off the actual data. Because when you say 100%, it's very much likely that you have overfitted your model and you are far from your real world pattern. And same for the underfitting. Underfitting is when you are trying to build very simple model, and it's way more simple that it actually misses lot of the lot of real world scenario. So here you will see that your training accuracy will be too high. Here your training accuracy will be too low. Let's say I build the model with a probability of 0.50%. I mean, why you're building the model with probably 50%? You can just toss the coin. It will also give you 50% probability, right? So it doesn't make the case that you want to like build a simple model which has only 0.50% probability, because instead of building the model, you can just toss the coin and see the answer. So 0.50% as an example is very underfitted model. You are not learning the green line. You are not enoughly learning the real world green curve, and you're gonna make a lot of mistakes. So this is underfitting. So underfitting and overfitting are the main problem while you are building the model. And when you come with the accuracy, when you say the too high accuracy, too low accuracy, you don't want to do with them. You want to be spectacle with them. Too high accuracy means you overfitted. Too low accuracy means underfitted. You need something which looks like this. Let's say probability of 85%. 85% is very good probability, because 85% is something like you have trained the curve which is very close to actual, And if you see here, you're missing only a couple of points, but by missing this couple of points, you are being flexible, and at the end you will end up with the model which is like, um, which is close to the real world scenario. Now, when I say 100%, that means my curve will satisfy all these data point. When I say very less than 50%, or let's say, less than like a small probability, a small accuracy, that means my line is not touching all the data point. And when I say 80%, that my line is touching almost 80% of the data, basically. So this is the difference between underfitting and overfitting. So when you're evaluating your model, you want to really look for probability, which is somewhere around 70 to 90%. You don't want to go for 100% more than more than 90% or less than 70%, because these are both the scenarios where you are either overfitting or underfitting. Same in the case of classification. So when you do overfitting in the classification, you end up with this kind of some kind of line, very weird, which try to satisfy each and every data point, and you might lose out on, because like you're over optimizing that, and your new example may not be where it's supposed to be. So this is like very crazy, and you will lose a lot of accuracy when you are doing example that you haven't seen before. And underfitting also same thing. Like if you are making your line too simple, then also you're gonna like make a lot of error, and the model that you build, which is this line, the line which tells whether it's a true or false, or yes or no, is gonna make a lot of error in the actual data set. You wanna look for something like this, which is do reasonably well. It is making very few mistakes, but most of the cases it is well, and it is very accommodating to the data that you will not see in future. So somewhere around 85% or 87% or 82%, or like somewhere like 73% looks like a good probability, because you're making some mistakes, but you're ending up with something, a model which is much more gonna satisfy your upcoming or future world problems. So this is your underfitting and overfitting difference. Now now we are done with all these theories, like very basic essential theories. Now let's look like how a machine learning project look like. So when someone is building a machine learning project, end goal is, first thing, he has some kind of use case. You always start with a use case, what you want to do with your model. If you don't know what you want to do with the model, you will not, it's doomed to fail, basically. So let's say I want to build a model which will tell me that if I give some person a loan, whether he will repay or not repay. So I have past customer to whom I have given the loan, and I know that who they look like, who those customers are, what is their average income, what is their age, what is their background look like, what kind of job they had, which neighborhood they lived in. All this data I already have, and I know the answer that in the past with this profile, whether they repaid a loan or not repaid the loan. So I have this data set. I know the problem that using this data set, I want to build the model. So in future, when I have some new customer coming in with this, for whom I will know all this information, and I want to predict whether, looking at based on my model, whether he will repay the loan in future or not, and based on that I want to give him a loan or not. So my end goal here is, if I invest in this project, and if I this model, and if this model will help me accurately judge whether I should give loan or not, then probably I will be optimizing giving loan to much more people who will be able to repay, and giving loan less to people who will not repay, and basically optimize my final income, because I'm earning from giving the loan. I want to give the loan, but I want to default, because giving the loan will make me money, but someone default, I will lose a lot of money. So I want to build a model which tells me that whether I should give loan or not, and this model will help me to judge it well. And if I can judge well, then I can make a lot of profit, basically. So this is all use case, this is all like requirement, and this is all we know. Now what I need, first thing is collect data and process data. So collect data and process data, this is how we normally start with. If you're a data scientist, you first talk to your database engineer or data engineer, that, hey, I want to work on this problem. I need this and this information about the customers. And you already have this thousands of data point, your bank know a lot of about you than you think of. But to know that whether you will default or not, I don't need to know everything. I just need certain information about you, and that's using that certain information I'll build the model. Now how I know that what information I need, or what are the features that I need to build the model? Because I'm a data scientists who also know the finance well, who also know the banking well. So that's where data scientist also has to be a domain expert. I'm a domain expert in the finance, I'm domain expert in the banking. I know what what are the what are the features which will help me or which will impact my, what are my independent variable basically, that will be, that will affect my dependent variable. So you go to data engineer, you take all this data, and then you pre-process all the data. You do this numerical, categorical, null value fixing, average processing, dropping some data, all this like pre-processing that we see yesterday. You do all that, and you finally build your machine learning models. Now you don't build one model, you build all the models, different kind of models, and you pick the one which come out with as a best output. So right now there is no like, so if you are studying algorithm, you know that, hey, if I want to let's say do the sorting, the best sorting algorithm out there is a quick sort, because quicksort, it does well in general. It's a faster, it has log n complexity and log n complexity. So that there is mathematical proof of there which says that this sorting algorithm will perform best compared to something like bubble sort, which will always perform worst. So that, like, but in machine learning world, there is no one model better than other model. So what you have to do, because you don't know, you just build different models. Like you just take all this model, you take a support vector machine, you take neural net, you take probatic model, you take linear model, tree based model. It's not like one model. Tree based model is category of models. You have tons of different kind of configurations in how you build the tree based model also. So so there are so many tree based models. So you pick all these tree based models, you pick all these linear models, you pick all this probability model, neural network model, support vector machine model, and finally you throw data to all these models. You see how each model perform based on their values, and finally you validate. So this is how you pick the model. Build 10 models and see which one is doing better in terms of accuracy, which is like satisfying my 80% probability range and doing better than other variables. And finally you go to validation. Validation is where you try to understand why your model is doing some kind of predictions, while it is doing some kind of predictions. Now, why it is important? Let's say your machine learning model uh, denied someone a loan. Your model said that, hey, I cannot give you the loan, and it's just yes and no answer. If your model is black box, you don't know how it works and what is actually going on inside it, then someone will come and sue me. Like, let's say in US there's a racism is a huge thing, and let's say a bank denied a loan to a black person. The black person says that, hey, you are a racist, you are not denying, you are being a racist and not giving me the loan because I'm black, you are not giving me the loan. But you say that, hey, but it's a model. But that person, no, it's you, it's not model, it's you. You are like, being, because I'm black, you're doing this to me. So how you defend yourself? So you need to make your model understandable. You should be able to tell that, hey, look, i I have this model, and this model has a preference that it look into neighborhood do you live in, and based on the neighborhood and past it, I can say that the neighborhood you are coming from, and the income that you have, and the let's say the job you have, all these data point and probability associated with all these features tell me that I should not give you the loan. So you can explain basically why I'm not giving you the loan. I have this data point, I have this model, I have this reason. So I can also do cross validation. So this is where someone come and sue me. But also, let's say I'm building the model, I want to make sure that my model is not biased. So what model is basically? It is a model is basically the pattern that it has learned from the data. If your data has bias, let's say your data has very few examples of black people, and in all this example, it says that black people will not pay the loan. So my model that I built end up with the model which says that no black people will ever pay the loan, and I will reject every one of them. I need to know that beforehand before I deploy the model. Otherwise, every black people I'll be rejecting the loan. I'm losing value, I'm losing business, but I'm also like creating a risk that that guy can come and sue me, right? So before I build the model, I need to validate the model. I need to understand why model is performing the way it is performing, how it is not biased, how it is very well documented and pass all the regulations, because all these problems. Because if you're in regulated industry, let's say you're building the model to predict that whether this person has a cancer or not. Imagine if you say someone has a cancer, you say that, hey, you don't have cancer. What happened will that guy, this guy will just live normal life and dying out of cancer, if, because he thought that he never had a cancer. Or let's say someone has a cancer and you say that, hey, my model says that you don't have a cancer, and you say that, yeah, hey, my model says you have a cancer. You're gonna probably doing the chemotherapy on the person who actually don't even have a cancer. So just like putting out there, like all the scenarios are there. Industries are very regulated, and they need to know if you are deploying the model, if you are using AI, you can very well understand. You understand what your model is doing, and then only you can automate. Because what model is basically automating the job of a doctor, model is automating the job of your loan allocating officer. So you need to take care of all these things. So this is where monetization comes in, and finally deploy and maintain. So your model over the time, the world will change, the scenario will change, things will change, and you want to keep your model up to date because the model is looking at the data at certain time slot. Let's say 2015, my model is being on the data or 2015, and now it is 2019. 2015, 2019, world has changed a lot, and my model has to update with this new scenario, this new pattern. 2015, let's say, software engineering was not paying so much well, but today software engineering is paying so much well. So like software engineer in 2015 will not be able to pay my loan, but software engineer in 2019 will be able to pay my loan because now the scenario has changed. So with real world things change, so you have to like continuously monitor that. So when you realize that you have to change the model, you're continuously monitoring the the performance of a model in the real world. So I predicted for this guy that he will pay the loan. Down the line, I will check that whether that guy actually paid the loan or not. And I'm trying to like over the time and try to like looking at my model and looking at the accuracy after like on based on the like newly learned the values, and then I say that hey, my model is making a lot of mistake now. That means there's new real world scenario, and I need to change my model. So you change the model. So basically, that is what deploy and maintain means. And if you are data scientist, you either working in this particular one small area based on how big your team is. If you are a single person, if you are a single data scientist in your company, you have to do everything. If you have like 100 data science team, you're probably working on one very small thing in the whole pipeline. Okay, so I'm gonna now showcase one of the example. This is the example. This is something which I did as I was talking about, like when I was doing my master's here in US 2 years ago, and I took the data science course, and we are working on this home credit risk. So home credit risk, what basically I'm trying to do here. I'm trying to basically this is the problem that I have. I want to predict that how many people who are applying for the home loan will actually repay the loan and will not. Like basically the example I was saying that, but the use case here is a home loan. Like this particular loan is basically on the home. So should I give this person loan or not? So this is my aim. Like I should predict how each if each capable applicant is will be able to repay the loan or not. So here is like zero means can't pay, and one means he cannot repay. Zero means he can repay. So basically, this is my binary classification problem: 0, 1. And so what are the basically tasks here? So first thing is data cleaning and processing. So that is the process, because you collect the data, then you have to clean the data, null value and all this kind of stuff, numerical, all this stuff. Then you compare between different models. So linear model, decision tree is one kind of tree model. Random forest is also another kind of tree model. Extreme gradient boost is also another kind of tree model. And finally SVM. So these are like number of 5 models which I picked up randomly. Right now, just like something like extreme gradient boost has been doing really well in real world right now. So a lot of people are doing a lot of extreme gradient boost regression model. So clean the data, build the model, and find RMSE value. RMSE value is basically computing the accuracy of the model. So this is so here I'm just doing step 1 and step 2. There is no step 3, and there's only part of the step 3 here, and there won't be step 4 because this is just like, it's a presentation. So you build the model and you show that you are not like maintaining the model in real world. So that is not part of this presentation. So now I know what is my data and what I need to do. Now what I'm going to show is this next 2 slide is like, this is going to be most of the time I'm going to spend on the next 2 slides, and like really pay close attention to this next 2 line, because I'm going to showcase the real world pipeline when you're trying to work with the data science problem. So here it is. So the first part, so there's 2 part here, data cleaning and building the model. So first part, you collect the data. Now data set, it could be one data set, it could be multiple data set, but at the end, when you have all the different data set, you collect, let's say there is one table called person, there is one table called his financial history, another table his credit card history. So you use all this table, merge all this table and create this single one table data set, and you start with that. So first thing, you deal with the missing values. So this is like first thing you do, drop by missing. So I'm writing here drop by missing, but basically, uh, you can basically treat the missing data. You can either fix the missing value or you can drop. There are two options. We saw that yesterday. So basically, you deal with the missing value. That is the first step ever. Now, next step is something called category. So next step is you're gonna treat numerical and categorical differently here. Now, why numerical and categorical you're gonna treat differently? Because there's different pre-processing for these both values. And so let's deal with the categorical value. Now, when you take the categorical value, you do something called one hot coding or hot coding. Now, what is hot coding? Hot coding is basically you take the categorical variable and you convert them into numerical variable. Now, we will see how we do that. But basically, what we do is, let's say in the categorical, you have three categories. What you do in your data set, you for all these three category, you create three column, you add three column for each of the category, and you say that whether this in my data set, let's say category low, medium, high, and I create the column called is low, is medium, is high. I added three more columns for each of the category, and then I put 0 and 1 based on in what category it was true. So probably in these three column at every time, only one of the column will have 1, but other two will have 0. So this is one hot coding. You take categorical data, you find out unique values, and then basically for all each this unique value, you create the column, and each column for each column you basically do 1 and 0. That's why it's called one hot coding on hot coding. There are multiple ways to do hot coding. One hot coding is putting 0, 1. You can also do something like you can, let's say, you can replace it with 1, 2, 3. You don't make three column, you only make one column. But now, because you know that you remember this ordinal and nominal, ordinal is hierarchy, nominal is not hierarchy. So let's say you have ordinal data set. So ordinal data set is a hierarchy. So what you're gonna do, you're gonna assign value 1, 2, and 3. So it's saying that 1 is a like low and 3 is a high. So now you have converted, you transform your, you transform this idea of category into numerical space, and you also transfer this idea of hierarchy by giving 1, 2, 3, which has inherent, like increasing, like there's inherent meaning of 1 and 3, that 3 is greater than 1. And when you have nominal value where there is like there's no there's no male and female, there's no idea of hierarchy going on. So there you want to do this one hot coding instead of giving them 1, 2, 3. So because there's no hierarchy going on, so when you represent that column male female by numbers, you basically do 0 and 1. You can create actually only one column which says like male and female. So 0 is male and 1 is female. That could be one of the way to do hot coding. Or if let's say you have three categories, let's say disease type, you have 5 disease types. So you want to create 5 disease type column, and then you want to put 1 and 0 based on which one was a particular categorical value in that particular row. So this is about one hot coding. We'll see one example. And with the numerical, we'll do fill missing. So how you want to do? So with the numerical, as you know that you saw yesterday that with the numerical, there could be different meaning of what the missing value means, and you're going to replace. So let's say in case of age, so how are you going to replace the age? So let's say you're going to replace the age, missing value, missing numerical age with just an average of age. That's something you can do that. And let's say now you want to replace something called whether he owned the car or not. So age could be average, and car would be also like probability, like hey, how many people own the car, how many people not own the car in the full data set, and based on that, I'm going to assign 0 and 1. So there are multiple values that you can. There are multiple ideas how you want to fill that particular null values. So when you have numerical, you do all the null. Now categorical will not have null because all the category will already like there's no idea of null in categorical because there is a null in the category that will create extra category. So when you do one hot coding or like hierarchical coding, there is no null there because you are basically converting whatever categories are there into 0, 1 already. So you don't need to do null because there is no null when you are doing hot coding, and numerical is raw data, so you do fixing. So now you have data ready. This is the point when your feature engineering is done. Now you may add more feature. This is not feature engineering. This is all data pre-processing is done. You have processed your data. Now you can look inside the data. You can understand the data, and you can think and look at the biases and look at start getting feel of the data. So this is the point where you start understanding the data by creating charts and graph out of the data for each column. But this is the point where you kind of like massage your data, you kind of like treat your data, you kind of fix your data. Now you have massaged your data, treated your data. Now you are trying to understand your data. Now what we do now, we do something called feature engineering. So this is where you start a feature engineering. First thing what I want to do is a feature importance. Now what is feature importance? Now you saw that we have different features while building our models, but not all the feature will highly impact your target. So let's say basically same example, credit loan. You're trying to predict your target here is whether he defaulted or not in the loan, and you're looking at all this column, and the one of the column says that let's say which city he's living, Boston, very generic city, or Surat, very generic. Now, if you want to understand how much the city impact the value of whether he repaid a loan, so you want to figure out like there is a city which you may imagine it may not have so much impact on figuring out whether he defaulted or not, versus something like let's say salary will have huge impact whether he repaid his loan or not. More salary, better chance of not defaulting. So this one feature which is called lesser salary will kind of have high impact on the result of your model, and you have this something called city which has low impact on whether you will end up demo. So different feature will have different kind of impact on your final model, or differently they are all these independent variable have different kind of interaction or different kind of dependency on a dependent variable. So with feature importance, you want to figure out how much your independent variable is dependent, how much dependent variable is impacted by independent variable. Now how you do that? So basically very simple idea. You see that if how much my value of predictions change with the change of my particular value of my column. So let's say I say that, hey, I'm looking at this, so I'm trying to figure out how much important this particular feature is with my final column of my target. My final target is let's say the loan, whether he repaid or not. So I'm looking at the city. So what I'm going to do, I'm going to create this only, I'm going to take these two column, I'm going to take all this city, and I'm going to take all these predictions, whether he defaulted or not. I'm going to see that if I change from Boston to Surat, how much change I see in my output, in my predictions, how much it impact how much it change my prediction value as an output. So if I see that even though I'm like the overall average y value in Boston is very similar to overall high value in my let's say Surat. So basically, like even though I'm changing from Boston to Surat, I don't see too much difference in my average target or average whether the someone is defaulted or not. So I go as these different categories, and I go as these different numbers, and then I try to see that if I switch from when I'm varying my number, how much varying my number in this particular column will also vary my my prediction values. If changing these numbers will not vary my prediction value, I'm going from let's say 0 to 10 in my age, but I don't see dependency, like my prediction is not changing too much with the rate at which I change. So basically there's not too much dependence. But let's say I have salary, low, it says that 0. As I change my salary, the value increase. There's a huge dependence I see between my salaries, the value of salaries, and my predicted the final output. So I can see high dependency. So that is how you calculate based on based on this value. So there are multiple algorithms. I told you about this permutation based algorithm, where you try to vary your values and see how much varying your values of feature will vary your dependent variable or your target. If it's too much varying with the change of then it's more dependent. If you change this a lot but this doesn't change too much, then it's not too much dependent. Now why you want to do that? Let's say you have picked up certain features, and changing that feature does not even impact, or which will have very less impact on your prediction. So basically these columns are not contributing anything in my predictions, so I'm just going to drop those columns. So I'm going to do the feature importance. I'm going to figure out, hey, what are my top features which are impacting, or which are like impacting my predictions, and those which is a very least impact on my target, I'm going to drop them. So this is feature importance. And this will also help you understand why your model, your how your data set look like. If your data set is like, hey, I mean, I can see that my data set is too much depending on this particular like values. So we are also trying to understand, how what your data is and how your data is impacted, how it is, how much dependency going on. So we are trying to understand your data also while building the model. So feature importance. Now, why you want to do like feature importance? First thing, because you want to understand your data, and second thing, you want to drop the column. Why you want to drop the column? Because when you are working in a real world scenario, you will have tens and thousands of columns sometimes. I have seen data set with 20,000 columns. Imagine 20,000 columns you are building the model, 20,000 dimensions, and every time you add one more dimensions, you're adding the more layer of complexity in your equations, or adding more layer of tree in the hierarchy. Like the more feature there, the more complex you are. So to save the space, to save the memory, to compute your to compute your model faster, you want to have least amount of feature which has maximum impact on the target. So basically, for the simplicity, for the faster optimizing your processing time, optimizing your memory usage, you want to drop this unwanted column. Okay, so now that we have final data, we have all the data now. Now we are ready to build the model. Now, if I when I'm building the model, what I want to do first? First thing, I want to split my data into training and testing. Why I want to split that? Because when I train the data, I want to figure out how much accurate my data is, and how will I know how much accurate my data is? So I can only tell how much accurate my data is if I test my model on the data that my model has not seen before. Remember, overfitting and underfitting. If I am using 100% of my data, so I have already overfitted my model. I mean, I'm building the model 100% of my data, and I will not know whether I'm overfitting and underfitting because I have no unseen data. I mean, if I have to test my model, right? I don't have unknown data. So to test the data, I need to use whatever data I have. So if I use trained data, so it's gonna tell me that, hey, it's gonna give me over optimistic answer, right? So this is like the scenario of overfitting. It's going to tell you, hey, my accuracy is 100%, but it might be overfitted because I haven't tested on unseen data. I will only know whether my model is overfitted or underfitted when I do the testing on the data that is unseen, and unseen means data that is not used to build model. Data that is not used to build the model, that I will use to figure out whether my model is underfitted or overfitted, or which will give you better idea of my accuracy. Because if I am testing my model, if I'm testing with the data that I also use for training, it's gonna give me the accuracy which is not real world example. Because as soon as I will see unseen data, so unseen data is where my actual accuracy look like. I want to see the better accuracy in my unseen data, not on my seen data, right? So that's why you split the data and you keep 10%. You can vary. The best practice is 80-20, but you can do whatever. So I'm doing 19 and 10, and then I'm splitting the data. So test data, I will not build the model. I will only use the testing data for calculating the accuracy of my model, and I will use trained data to do the whole thing. And here I'm building the regression model, and then the tree-based model. Now, if you see, you can see something called standardization. Now, what is standardization? This is very important concept. Now imagine you have two columns. One is the age and one is the salary. Your salary will have values ranging from, let's say, 0 to 10 lakhs. And your age is only ranging from 0 to 120. Now you see there are very two different scales. But imagine if one variable has a huge scale and one variable which has least scale. So when you're building the model, the one gonna end up making more impact on your model, and one gonna make keeping less impact on your model. But ideally, although they are salary and age, both feature has to have similar impact in a final model. My model should see equally how much important my age is and how much important my salary is. But because intrinsically they both work on different kind of scale, you end up with the model which gonna give more importance to the salary because it just see bigger number in salary, and not gonna put a lot of importance in age because you don't see too much big number of age. So how to fix this problem? So what we do something called standardization, where we take all these numbers which are in different range and try to put them in same range. So let's say I take the salary and I put them into 0 to 1 range. I take the age and I put them into 0 to 1 range. So standardization is the process where you take all this number on the different scale and try to bring them into same scale. So they all are seen equally by your model. So that is what standardization look like. So that is something very important when you are building the model. Now that you have done the standardization, now you need to do training. So train and test both has to go with the similar kind of process, because same data will be used here. So now that you have done the standardization, so now some of the data doesn't need standardization. So linear model is sensitive to standardization, but tree-based model are not sensitive to standardization. So if you are building a linear model, you want to do standardization. If you're not building linear model, you can skip this stage, because decision tree can still have different age and salary working on a different scale and see them equally. Your linear regression, which is basically equation a plus b plus c, is see all number equally. So is gonna impact by this different scale, different of the scale. So because of the nature of the model, you have to do standardization, and because of the nature of the model, you don't need to do standardization here. So that is why there is a two different path here. So now that you have built all this model, you finally want to do predict. So what you do with the predict, your input is this model that you have built with 90% of data, and then you use this 10% of data. So this is the model, this is a test, this is test data, and you finally, figure out what is the test data, what is the test probability look like. So this prediction will finally give you an output, like, in 0 to 1, or it's a categorical problem, which is this problem is categorical problem. So output will be the value between 0 to 1, and I will have some kind of cutoff. Let's say 0.6%. I will say that points more than 0.6 is he will default, and less than 6 he will not default. Something like that. Because model will only give me probability, I have to figure out what is my breakpoint, and above the breakpoint yes, below the breakpoint no, or diabetes no diabetes, will default not default, something like that, in the categorical case use case. In the linear use case, you will just get the number. In the regression, you will just get the number, so you can just deal with that. Now I'm using linear regression, because linear regression can also do the classification problem. So don't worry, it's a linear regression, it is still doing the classification. There's a technique, it's called logistic regression. So I might have put logistic regression, which is same as linear regression, with one additional step for making sure that your linear is into this 0-1 range and categorical problem. And finally, that you have built the model, you want to do something called RMSC, which is like you want to figure out how your model is doing. This is the validation part. RMSC is your accuracy metrics. It's a root mean square error. So as you see, there is an error. So basically, you want to see that so in your test will have x and y basically. So what you want to do with the test, you give the test to x, your model will tell you this is what I predicted, and now you already know the actuals. So you have 2 of y actual that you separate from this, and y predicted, and you compare y predicted with y actual, basically 2 columns, 2 numbers, compare each numbers and try to figure out what is the root mean square error look like, how much on an average I'm making error while comparing these 2 numerical columns. So that is my root mean square. And finally, confusion matrix. So this is your end pipeline look like. Processing data, dropping non-important column. Once you have cleaned the data, you break them down in train and test, and then if you have to do standardization, you do the standardization, you build the model, do the accuracy, and then based on accuracy, you build this kind of like chart. Now I will come to confusion matrix. Confusion matrix is something for categorical problem. This is something only exists for categorical problem. Doesn't exist for linear problem, regression problem, or time series problem. And then RMSE is generic. It's a error matrix, and that error matrix could be done for. So this is something that we did, and like all this analysis that we did. I will just quickly show you the categorical thing. So we have this name family status, like this is one categorical, we convert to linear. How? Like we have this categorical where we says single, married, civil married, widow, separated, or not allowed, whatever NA. So we created column for each of them, and then you see that there is no like hierarchy going on here. So like if it's a single, it's a 1, all 0. Single, 1, all 0. Married 1, raise 0. So this is how we do one hot coding. Because now feature importance, so you can see that these are all the features and how much impact they are making. There are some pre-built algorithm. You can just apply your features, and it will tell you how each of the feature are impacting your target, and then you can pick that, hey, all these top features listed, like sorted by my feature importance will be important, so I'm gonna drop anything which is after this. Like this is all, I might have like, let's say 70 columns, but only these 20 columns are more impactful. Rest of the 30 columns I don't care, so I'm gonna drop them. Then this is like fitting the model. Descent tree model, random forest. I'm not going to look into all this SVM. parameters. I'm not going to look into PC also. Just PC is one of the way to reduce the dimensions. I'm not going to look into that. Now the RMSE score. So we got this different RMSE score, and it's an error. You want to minimize the error. So the low the error, the better the accuracy, basically. So you see that lower error you see in the random forest. So random forest seem to doing better. Your descent is doing kind of not so good. Your linear, linear regression is not doing so good. SM is not doing so good. Your RMS metric says that random forest is doing good because there is a error is very less. So you pass actual versus predicted. So actually is like in the test data, what was the actual value, and predicted what you actually predicted out of your RMSE. Now look at confusion matrix. Confusion matrix is where when you have actual and you have predicted, you try to see that how much far you are. So actual is like in my testing data set, how many times the result was actual and my model said it was actual. Like my model also predicted actual, and originally it was actual. Originally it was 0 is a yes and 1 is no. So in original data set, 0 said he will not repay the loan, and my predicted was also same. Like 94% of time, I was right for yes, and 0.05% of time I was wrong. I was also right. So like my actual was he will not repay the loan. My predicted was he will not repay the loan. And there are some other data set where my actual said that he will repay the loan. My predicted also said he will repay the loan. Now this is the error area. Error area means actually he will not repay the loan, but I will say he will repay the loan. Actually he will repay the loan, but I will say he will not repay the loan. So this is the error part. This is how much I was accurate, and this is how much I was wrong. Like actual was 0, predicted was 0, actual was 1, predicted was 1. So how much time I was right? Actual was 0, predicted was 1, so I was wrong. Actual was 1, predicted was 0, so I was also wrong. So these are wrong, these are right area. So right now I'm comparing all the models, and I'm seeing that in different models how many times and how many areas I was right and how much time I was wrong. Now you can see all these metrics. Now why I want to look at these metrics? Now imagine, so first thing, you can see that every model will have like different ways. Like my XGBoost has different, different like time I was right, I was wrong, and different kind of like I was right, I was wrong. So if you look at here, 0 time I was zero probability that I was, like 0 times I was, so I'm looking at error. So 95%, the actual was 95%, and so I was right here, and I was right here also. 0% data I was right, and then 0 and 0, 90% I was wrong. Now why I want to look at all these metrics? I want to look at this error. Now imagine here there is a trade-off going on. What is the trade-off? I can either pick a model. So if you see there, like a lot of models have similar 94 0.5, 94 0.5, 94 0.5. So probably 3 models are giving me that how much time I was right. Now I want to pick the model. So because how many time I was right is similar, I want to pick the model based on how much time I was wrong. Now here you can see there are similarity how much I was wrong. How much I was wrong here, how much I was wrong here, like 0.01%. 0.01%, 0.05%. Now why I want to look at how much time I was wrong. Imagine what we are trying to do here. What is our end goal here? I want to predict, should I give the loan, should I give back the loan or not? Okay. Now I'm happy with the model who will not give to someone loan, who will be able to repay. There's a guy who is capable to repay the loan, but because of this small error in my model, and there will always be some error in my model will say that no, I'm not going to give you the loan. I'm happy with that use case. What I'm not happy with the other kind of error. What is the other kind of error? My model says that this guy will repay the loan, but he will not. The cost of someone who is cost of wrong, where someone is like not able to repay the loan, and me giving him money, like the cost benefit is too big. Like I want to reduce as many cases possible where I'm losing a lot of money here, right? If I make the model which is more wrong towards giving up, more conservative towards giving up the loan, uh, more conservative in giving the loan, that is fine, because I'm happy. Even though I'm not doing the business, I'm happy, I'm not taking loss. But if my model is more liberal in terms of giving up the loan, then this problematic, because I will make more damage than profit by going off this kind of metrics. Okay, so imagine that, like That is how you need a data scientist here. That is how you want to compare all these matrices to understand how your model is doing. And if you look at the just pure probability, you may pick up the model who is much more accurate, but in general who might be much more liberal in terms of giving loan. And even though it was much more accurate than the other model, it was less accurate, but my less accurate model might be more conservative, and my more accurate model would be more liberal. And if I just look at my accuracy, I might be wrong, right? So that's why I need to be very careful about not going to pure accuracy. I need to look at other matrices, see why model is doing certain things, and pick the right model. And pick the right model might be not picking the model which is more accurate, but picking up the model who satisfy my use case. Now my use case says that I need to have model which is much more conservative, and don't just give up to make less error in giving the loan to the people who might default. Now, what is the other use case? The reverse use case. Let's say I have a use case where I'm giving the, let's say, discount coupons. I'm going to give the discount coupons. I want to predict that whether this discount coupon will end up with the customer coming to me or not. Now, imagine I'm much more liberal, or let's say spam filter, much more, spam is much more. I'm building a spam filter which will tell me whether this should be spam or not. Now, imagine the very inverse scenario. The damage of being more conservative and categorizing something as a spam is much more difficult. I'm the guy who never look at a spam mail, just tick and delete all the spam mail. Now, let's say if my model is a kind of model who is much more conservative, and whenever it is confused that it make more error in putting my important email into spam email, the damage is much more there because people are deleting the spam email. So in this very reverse scenario where conservative is harmful, I'm happy with being liberal. I'm happy if I'm not able to some of the spam email, if it is end up in my regular inbox, I'm happy with that. Compared to other scenario, I will be slightly annoyed, but I won't be that much annoyed if I end up deleting an important email. So here I am happy to be much more liberal. I'm happy to be keeping the spam email in my inbox versus throwing my important email into spam. So you see there, even though, so here in this case of confusion matrix, I'm leaning towards the model which is much more liberal. So use case wise, even though you can have same model, same statistic based on use case, you pick either you want some model which is liberal or some model which is much more conservative. So that's why the knowledge of data scientists come into the picture. And that's why the validation phase, the confusion matrix, or all this kind of charts and graph, or which is something called explainability of the AI is important. I'm personally the engineer who works in an explainable space, and the product that we are building, I'm part of the team where I lead a lot of projects where we add all this capability or different ways to explain the model. So one of the project I also worked in where I build the backend engineering process, backend stuff for giving the confusion matrix for the people who are using our product. So the idea is this is the explainability part of the model that also you need to look into as a part of validation. So here I'm like concluding my presentation, and let's look at some really good examples. Let me see what I have planned, something else. Okay, I will cover this very end, the difference between these two. So let's look at one example. So I'm gonna just showcase you something. This is not like, this is something I did for one of the session I did for an hour on parallel processing. This is basically the presentation for the building models in parallel, but it still covered a lot of concepts. So let me go to the code, and you can run the code, and let's first talk me about the problem statement. So this is the data set on the child birth in the US, and what we are trying to predict here is if there's a new baby is born, will he be underweight or overweight, or like this kind of like pipeline, like will he be like regular weight or not regular weight. So sometimes baby can born with like overweight or underweight, or they can be regular, like something that is considered as a standard weight of any newborn baby should be. So this is the model which predict that if some new baby is born, will he be like mal weighted or just regular, or properly weighted. Her or his weight would be like proper, or something that is expected out of baby. So this is what we're predicting here. Now you can see this is a classification problem. The proper weight or not proper weight, whatever you want to call it, these two categories. And how are we going to do that? So first thing, we want to do the data processing. Data processing means pandas and numpy. So we are bringing in numpy and pandas. I'm going to do a little bit of parallel processing. So just bear with me, but I'm using also the parallel processing library. And now I want to do all this model, the model building thing. So scikit-learn, sklearn is the library which has all these data science related methods and tools and all these things that you can use to build your model and do all the data science stuff that you want to do with your data. So we're gonna bring a couple of libraries from here. So scikit-learn, we are bringing model selection. We will see what we're gonna do with that. From scikit-learn.matrices, we're gonna bring something called ROC curve. ROC curve and log loss are something similar to what we call the um, like one of those matrices. ROC curve is area under the curve, which is like one of those another not confusion matrix, but similar to confusion matrix. There is another something called ROC curve, area under the curve. Basically, I'm not going to go into detail how it works, but one another matrix in parallel to confusion matrix. Log loss is one of the another matrix like RMSE. We saw RMSE. Log loss is basically another error matrix that tell how much error you're making. Now, with the model selection, I'm bringing something called train test split. We saw that we split our data 90-10%. So this is something that will help you to do that. And we're going to bring shuffling. So because we have data that's coming in, we're going to really shuffle the data. So we make sure that when we are doing training and testing, the data is well enough shuffled. And then finally, from scikit-learn ensemble, we're going to bring all these classifier models like random forest, extra tree. These are tree-based. ADA boost, which is like boosting. These are all, I think all of them are tree-based models, but these are all tree-based models they want to bring in. Now, there is this method which does data processing. I will come to this method later. This is another method which kind of give you how much accurate your model is. I will also come to this model later. Let's look at this. And there's this compute in parallel. This is third thing. There are three models we will look at later. Let's start from here. First thing, I want to read the data. So what I do, I read the data, and then I have this like process data for modeling. So I'm passing the data set, and I'm getting the data frame as an output. So let's see what we are doing in the processing data. So if you remember, first thing we do with the data is you read the data, and you do with the like some kind of processing. So here, gender list, you're doing the sampling, and you're mapping. So you're converting your male female to 1 and 0, one hot coding. This is not one hot coding. Yeah, this is one hot coding. So I told you that one hot coding could be just 0 and 1 if you have just one column. I mean, just binary choices. So this is what we are doing: data frame dot sex dot sample and dot map. If you remember dot map, we are basically like performing the transformation operation. And what you are doing with the map, that if it's a M, make it 1. If it's a F, make it 0. So you go into data frame, you go into this sex column, and in the sex column, you look at the M. If it's an M, you make it 1. If it's an F, you make it 0. So this is something you are doing with this line. Once you become like very good with the data processing, you just like start doing all these things, like multiple things the same line, like chain of operation. That is what we call it, like chaining, operation chaining. So you will get better with this. Now data.rename. So you can also rename the column. So here you are saying that I have this 2 column which has this weird looking name. So actually F raise 6 means a father's race, and M raise means his mother's race. So here in US it's very common, inter-race marriage is very common. So but that can be one of the factor, like someone coming from a black community, someone coming from Chinese community, and all these things factor in the baby's weight basically, because let's say a Chinese baby have different kind of idea of what is underweight, overweight versus a baby of some southern American white people, because they are like very huge people, just height and weight wise. So so because of that race factors, and race can matter because different race can have different idea of what is regular baby look like for them. For Chinese baby, the low weight will also be normal. For Southern American babies, the weight, something which is normal in Chinese would be less in Southern American. Now, what we have as a DWTD. So we actually have the numerical value of the weight, but what we want to do, we have this weight coming from, like starting from 0, which is like no weight, to let's say 50 pound, which is like 25 kg. Is too much, but just imagine like The weights are numerical values, they're continuous numbers, and I want to convert that numerical into categorical by telling that, hey, if the weight of the baby is more than this, then it's gonna be if the range of the weight of the baby gonna be in between this line, then it's a 0, otherwise it's a 1. So this is like lambda method, where I'm in the lambda method, I'm passing the particular number x, and if the x is greater than 2500, then it's going to be 0. So basically, if weight is more than 2500, just imagine it's a 25 lb, 25.00 lb, which is 2500. Then it's going to be 0, means it's a regular baby. And if it's more than that, then 1. This is very like, this is example. This is not like very perfectly solve the problem. It's not going to have best accuracy, but just imagine, for the simplicity, I'm going to not do a lot of like crazy stuff here. You can go as crazy as possible in defining what it means for you to be a regular baby, not regular baby. For the simplicity, we are just putting simple condition. If more than 2500, it's a regular baby, it's not regular baby, and if less than, then regular baby. So this is how we are like massaging or changing our data, dealing with the numerical converting into categorical, basically. Numerical like processing, like not categorical, but like converting the range of a 0 to some big value into 0 and 1 value. And this is going to be our target. And then we do some bit of sampling here, and then drop. So we have to figure out that, so I'm not presenting here, but through my analysis, I have figured out that these are the column I don't need. So I'm just going to drop this column here at this point. I could have dropped this column based on looking at how many missing values are, or whether by looking at the feature importance. I'm not doing any of that here. Just imagine that I did feature importance, I did null values, and these were the columns which are like less important, or maybe had a high number of missing values. So I'm dropping these columns. So now I'm done with the dropping columns. Here, get dummies. So pd.getDummies, what it does is basically take this categorical column and convert them into, do the one hot coding. So you saw that the process would be tedious, like, looking at these multiple columns, figuring out how many unique values are, creating extra column for each of the unique values. If you don't want to go through all this painful process, you can just do pd data pandas as this library get dummies, which will just take your data and automatically look at the unit and create extra column for that. So pd.get dummies will get you all this categorical column converted or being one hot coded into numerical, and finally you get data frame. And drop first equal to true. So basically, when you already converted at append, like basically you are doing append operation here. So you want to delete the append, like, because now you already have append being represented as multiple columns. So you want to delete this particular column. So that's why drop first equal to true. So like drop the append and then replace the append, and don't keep append once the dummy processing is done. That is why drop first. So now we finally have processed data, very well, very fine, numerically well processed. Now that we have DF, now what we want to do, we want to create the train test. So this is the DF, which is slide 1. So what we saw in slide 1, we are done at this point. Now we are moving to slide 2. First thing that we did in slide 2 was doing train and test split. Okay, so basically X and Y. So how we gonna do that? So basically, your X and Y, X is your training part and Y is your testing part. So what you want to do is you want to take the data frame. So like you have n columns. Now what you want to do, you want to take that one target column out and only keep the column which is called X, or your training data set. Or so Y is your independent, that last column, and X your all the independent column, and Y is your dependent column. So remember that table, the decision of going to play or not play, you're taking it out and storing it Y, and you're keeping all the other data. So basically what you're doing, I'm going to take the DF, I'm going to drop this one column. So I'm going to end up with a data frame which will not has this target Y. Now this is my X. And then I'm going to create one more data which will only have df dot target column. So basically splitting columns, splitting the whole data frame into n-1 and n. You're taking out the target and storing into Y, and you're taking. So now you have splitted your data into. We are not train test. This is like training and validation data. Basically, X will be your training data. I mean the data on which you wanna. Data on dependent and independent. Sorry, X is your independent variable, Y is your dependent variable. So you just splitted your data frame into two: list of independent and that dependent variable. Now what you're going to do, you're going to train test split. So this is coming, train test split is coming from, if you remember, scikit-learn model selection. So this is the method. What it will do, it will take X, it will take Y, and it will take test size. So I'm going to say that I'm going to keep 33% as my testing data and 66% as my training data. So now it will going to give me X train, X test, Y train, and Y test. So basically now this X, so if you think about the table, so there was this huge table, square table. Now this square table, I took out this one column. Now it has rectangle, like n minus 1 and this one column. Now this n minus 1 and one column, I'm again gonna like draw one more line. I'm gonna say that this is my X for the train, this is my Y for the train, this is my X for the test, and this is my Y for the test. So you're splitting train test, and you're basically getting this X train, X test, Y train, Y test. And now that you have all this data, now you want to finally do the computation in parallel. Just don't think too much, like just imagine that right now we're going to start computing. Okay. And here, what I'm trying to do here, I'm passing different models in this parallel computing framework, and then it's going to just like take this data and build multiple model in parallel. You can look at here, like basically what I'm like, this is a compute in parallel. I'm passing the models and I'm passing the method to compute the error, and it will give me list of errors for each model mapping. So these are input, two things, and then one I will get an output array. My input array will be model and method, and output array will be, we'll look at later. So let's look at the we are here. You're calling for computing parallel. Inside the computing parallel, you're doing this map, and you're basically doing the going to models. Find models, like find the error. You're basically computing, like build the model and give me the error. So CLF equal to model. So whatever model I'm passing here. So right now I'm passing all this one by one. So I'm passing random forest. So this may make more sense for model. So I have this 1, 2, 3, 4 models, and I'm passing the model object into the find log loss. So these both are just two different versions, parallel version, sequence version. Let me talk about sequential. This will make more sense. So in this method, I'm passing the model. Now model comes here, and I'm going to say CFA equal to model. So this is a function object. You remember object and object method, object and method. So I'm passing the object. Here I'm like calling the object, and CLF equal to model. So it will give me like instance of this class variable. So this is actually model is actually class. I'm instantiating my class here. So this is the class instance CLF, and CLF will be different for each of the models. So I'm gonna get 4 different CLF, different call. Now every model will have this method called fit. Fit will take X train and Y train. So it will because learning by example, it's a supervised learning. So you tell them, this is my independent variable. I want to build model using these variables, and this is what you will use to build the model. So look at my answers and build the model using this variable by looking at the answer. So basically fit will have X train and Y train. So you are giving them all the independent variable and final dependent variable. Finally, when you do the fitting, you end up with the model. Right now CLF is being trained, and like it has already internally built the model, and if it's a tree, it has built the tree already. If it's a line, it has figured out the whole equation already. If it's a naive base, it has computed all the predictions. If it's a SVM, it has done the splitting and computing the hyperplane. So whatever way the model has been built, it's a lesson neural net. It has like configure all the weights for your neural net. So basically the model is ready now. Now what you want to do, you want to do predict. So why to do predict? So now you want to see the performance of your model, and performance of your model will be done using predicting on the data that you have seen. You have built the model using x.train. Now you're gonna test the model using x.predict. So x.predict gonna give you predicted value. Like if I provide unseen data, what my model will give me as an answer at what my model is right now. So y output. So this is my predicted values. Now for x test, I already know originals. So what I'm going to compare my originals with what my model threw out as a predicted. So log loss. This is like this also coming out of it's a simple like log loss is a simple method coming out of scikit-learn.matrices. And what it basically it basically take 2 columns and just give you the log loss matrice or that array number based on how much difference between those 2 columns are. So that's what we end up with, saying that this is the error in my model. So this is like train the model, predict, and finally find the output. Now, if you remember the standardization step, we are not doing any kind of standardization here because this is all tree-based model. And if you remember, tree-based model doesn't really need standardization. So that's why we are not doing here. And finally we end up with the model, and also we end up with the what error that particular model has. So let's just run this whole thing. Uh, Let me just do one by one. So importing all these, processing data, finding log loss. So this is just, I'm not starting computing, I'm just loading the method, defining the method. Now here I'm loading the data. Here I'm doing all the pre-processing and doing the train test split. Random forest is not defined. Okay, scikit-learn, no module name. Okay, probably I need to install scikit-learn first. Sorry, this is like new. Anyways, I already have some results. So when I will run everything, it will like start computing. It will end computing, which tell me that this is my log loss error. So if you can see here, all this error for different models, you see the huge error number. It's not in terms of 0 point something. It's in terms of now log loss is another metric. So log loss has something when you do the log of the data. So it kind of like log loss is basically, so log, when you take a log of big number, what log basically does, it kind of bring down your range of data. It's kind of like the scale of your data is being brought down. So when you are saying, hey, give me log of A, so basically based on like log of 2 or log of E, you are bringing down the scale of your data from, let's say, 10,000 to the scale of E or scale of 2 when you say log of 2 or log of E. So log is basically, standardize, in a way it's a standardization, bringing down the scale of your data result that you get. So log loss will tell you all this error, and it's a scaled down version of the error score, and it's a loss, so you want to keep the loss less. And because we haven't done so much of, we are just like doing the bare minimum, that's why you see a lot of error here, and that's why you see these big numbers and not like something in terms of 0.0 something, because we haven't done enough feature engineering and stuff like that. So this is your final output look like. Now you can also do like, you can create confusion matrix, and there are inbuilt method that you can use to create confusion matrix that you can do it. Okay, so scikit-learn, this. So I'm doing train test split. This data set is like almost 600 MB, so it won't take too much time, but it will still take some time. And finally, I will build my model. Or you can try this automatically. Just keep running all this step. This will basically install the package that you need, and then you can do it by yourself, and you can see the result. So hope this all makes sense. Now I want to end this presentation with this one final slide. This is something that I see a lot, like a lot of people who are dealing with the data. People are looking for different kind of job, and they're applying for something different than who they are. So there is a very different category, different problem, like who are data scientists, who are data engineers, who are data analysts, and if I'm looking for data analyst role or data engineering role, what exactly skills that require to work in that role. Data analysis are known as business analysts also. So these people are the people who understand business very, very well, who know the statistics, who can pull the data together, who can build different kind of like, who work well with the SQL, who do the Tableau. These are the people who sit with the executives, or who sit with the people who actually build all kind of dashboards, all kind of like charts and graph for executives or for the decision maker to consume. So these people are not tech savvy people. These are data savvy people, but very, very well MBA guys who also know how to deal with the data, and who use so many of drag and drop kind of tools like SAS or Tableau or Excel. And these are the people who use this kind of data. Now the strong skill these people has, data analyst has, is strong understanding of business problem, forming business use case, and trying to figure out what is the cost benefit of working on one problem versus another. So these are very much people who work with the requirement side of the whole data science pipeline. So these people are basically tell that, hey, we can do data science project, and we can work on this use case, and we can solve the problem. They are not going to build the model, they are not going to collect the data, but they're going to work on this particular requirement, work on this use case, and tell that, hey, I'm a data analyst, and I can tell you what are the problems that are important enough that I can work on. So I will say that I'm gonna do one metaphor here. So let's say you are the, let's say you are North Korea who want to nuke United States, and now you want to figure out which state you want to nuke. So how you start? So you have, first thing, you have a radar. Your radar, sorry, let's not say we wanna defense our system. Let's take this metaphor. We wanna defense our airspace, and in the airspace, what we're gonna do, like if some missiles comes in, I'm gonna throw the missile and I'm gonna accurately uh, drop down certain missiles, a certain aeroplane that is coming from the enemy to my territory. So what I want to do? First thing, I need a radar. Radar will keep lookout for all this problem, and you can say problem are those aeroplane data coming into my area. So data analysts are basically the people who are looking at the problem statement. They are not like rocket scientists. They are people. Radar is kind of like people who are like just looking around, seeing where the problem lies, see where the opportunity lies, and see where we can invest in like where we can invest in throwing the missile. So data analysts are basically like a radar who are looking for the problem, who are looking for those enemy planes coming into your picture. So these people are not very scientists. They are just good with understanding the problem, understanding the plane, and understanding that this could be a threat and I need to take care of that threat. Data engineers are people who basically create the ammunition. Ammunition means like who create the whole whatever sulfur or whatever, like the thing. So what data engineer does, so once data analyst says that he want to work with this problem, data engineers in general independently just maintain the data in the data set. You are running the website, you are collecting a lot of data, you are you want to make sure all the data are well placed, well organized, and is readily available. So these are the people who normally sit on your data, who are the data admins, and make sure that data is flowing in well, data is maintained well, data is archived well. Just sit on the data and make sure the data is well. These are the people who are data engineers. These are the people who kind of sit between data analysts, data scientists. Data engineers doesn't has to understand business too well. They may know some bit of understanding of business, but like they are not the people who are able to know good business side. These are the people who are expected to have very good computer science knowledge, very good software engineering skills, because they're going to build a lot of system for maintaining data. So these are the people who normally work with the Hadoop, Python, NoSQL language, lot of database. They are not the guy who work with the Tableau and SAS. These are the people who work with the, OLAP Cube and MS SQL Server and like the big database. These are the people like Hadoop and maintain the data and work with the data. And final, data scientists. So data engineers are they are the people who kind of build the warhead. So in terms of missile, the warhead is like the actual nuclear bomb or whatever, the bomb part of the missile, because missile is the carrier. Actual bomb is that one square thing that you put inside a missile. That's the bomb. So these are the people who actually carry the bomb. These are the people who actually build the bomb. In our case, the data. So, and finally, data scientists, who are actually the people they are like the nucleus. They are the people who are like finally build the missile. These are the people who throw the missile. Now you understand that the complexity of the problem and how much stakes are in place. Data analysts can look at the plane and like they are thinking about the data. So they can look at multiple planes and they can figure out the cost of investing into data analysis is very less. There is very less effort required to figure out, whether the incoming stuff is a plane, is the enemy plane, or is a bird. So it's not that much difficult problem. So data analysts can like in terms of like they can be a bit of like not so tech savvy, not so like math math wizard. They don't need to be math wizards. They are good speaker. They talk well. They know things well. So like they don't need to have the very high mathematical skills here, statistical skills here. Data engineers kind of sit in between. They are the people who build the bomb. They are the people who sit with the data. So it's like they need to be more tech savvy than data analyst, but they don't have to be a like statistical wizard or math wizard. They know algebra well. That is good enough. They know what is join means, what is inner join, outer join, all this linear algebra stuff. They're good enough. They're far better. They don't need to know about probability. They don't need to know about statistics. That is not their job. So they can skip that data part. So you can see that in the hierarchy level, these are the people with slightly more skill of technical, slightly less skill of other things. And finally, data scientists. Data scientists are the people who finally gonna throw the missile. These are the people who gonna put your warhead. These are the people who gonna design how a missile look like. They are the people who gonna accurately predict where this aeroplane gonna be from the moment I lose my missile to the moment it actually end up with the trajectory. These are the rocket scientist people. These are the math wizards. They work with the probability. They work with the like physics of all these aerospace physics. And so the idea is these are the people who know in and out of the model, uh, who know all these like inner workings of all these things. And that's how they basically, they are the like most tech savvy, most math wizard people. and uh, and these are the people who are finally uh, responsible for launching the missile, basing on deciding that, hey, this is a aeroplane, I'm going to figure out the trajectory of the aeroplane. If I will be flying my plane like slightly 20 slightly away from the plane, because when it reaches the plane will come here, and my like my rocket will hit it the right way. So understand, like, so this is how the whole thing is. Now understand the cost here. Data scientists are the people who are given very specific target. Data analysts are looking for the problem. Data engineering guys, once you need to know the problem, they're kind of like narrowing down. The investment is increasing here. Data analysis is less investment, just figuring out whether it's a bird or whatever it is. Data scientist, data engineer is more investment, because you need to like build the warheads. And data scientists are highest number of investment. They're most focused people. They know what they want to achieve. Data analysts don't know what they want to achieve, because they don't know. Their problem is look at the sky. That is the problem. Look for the problem, look at the sky. Very, very generic idea. Data scientists, I want to throw down that plane that is flying. Very specific. I want to build the model who use this data, who has this accuracy metrics, and it's gonna predict this thing. Very specific, very scientific base. They know exactly to the granular level of detail what they want. That is data scientists working on very level detail. And this is important because they go all the way down into complexity. So when you're investing in data scientist, it is important that you are working on the right problem. Imagine data analyst, it tells that, hey, it wrongly tells a plane as a bird, or as a bird as a plane. Now data analyst told that, hey, this is a plane, but it is actually a bird. And now a data scientist is like investing all this money, all this data, all this missile, all this like billions of dollars building this missile just to fire that bird is flying, because data analyst did the wrong job. So there is a value in data analyst. They hold their own space, but for them also it's important to figure out what is good, what is bad. That is their role. But their idea is they work with very broad probability, very broad space. Data scientists work with very least amount of space. And the thing start with data analyst. If they do the poor job, you end up wasting a lot of money, because your data analyst make you invest all this money just to fire up or take down that bird that was flying and not the aeroplane. So that is how all of them are important. They have their values, and they have the way they work, and the skill they have, and how much math wizard they have to be, or computer scientist they have to be, or business MBA degree they have to be, from one end to the other end, to deal with all these things. So when you're looking for job, and when I say you're data scientist, be sure that you are that guy who know all these things and who are working with right head there. You know your math, you know your model, you know all these nuances of the probability. If you're applying for data engineer, you don't need to know other stuffs, but you really need to know about the linear algebra, Python, Hadoop, and stuff like that. And when you're working as a data analyst, you don't need to learn about all the complex tree, and how the tree models are built and things like that. What is numerical, what is categorical, but you need to understand business very, very well. So these are different set. They are not the same thing. Different varies, different complexity, different areas they play with. So be mindful when you're applying for job and when you're building your career, what you're looking for. Okay, so this is it. Thank you very much. I'm concluding my presentation today with this. Let me stop sharing my screen. I hope this was like very, very useful. This is as much thing that I can fit in the least amount of time. So I hope that was useful, and I will really looking forward to see some of you guys try to attempt some kind of data science project as your capstone project. Thank you guys. Over to you, Ami ma'am. I'm gonna stick around, but now I'm heading over to you.